see. Yep. The stream is there. Everything is somewhat working. And let's see. I gotta send this to black pen, red pen. So hello everyone, to whoever's watching the video also. I'm gonna be doing abstract algebra, a speed run, and let's see. I need to. Oh, I'm already live. Oh boy. Hold on, what do I need to do? I need to send this link. Where's the link? Oh my goodness. Yeah, this thing is hard to work with. That's what I'll say. Okay, where's the stream link? Also, if y'all can hear other things, actually, hold on, let me check. Okay, yeah. Alright. So, let me... Where's the link? If you guys could, like, send the link in chat, that'd be really helpful. Because I can't really see chat that well. Hold on, actually, I know what to do. I'm gonna go ahead, open up a new YouTube tab. Go to my channel. And also, I know I'm a little bit quiet. So that is a link. Okay. Control C. Alright. Now let's go to Twitter. And I have to log in. It's not good. I don't really remember my login. Yeah, I know I should have done this beforehand. I'll get to the stream at 10:45 my time. In 5 minutes, I'm gonna start. 10:45. You can mark me on that. So if you're watching this on the video, just skip to 5 minutes to when I actually start. Is that it? No, it's not. Oh. Okay, hold on. There we go. So I might have to do stuff later on in the day. Who am I sending this to? Black pen, red pen, tweet at black pen, red pen. Oh my goodness, computer's slow. So hard to work with. Speed run. Boom. Alright. Okay. So we've got our splits. At 10:45 I will start. So just gonna mentally prepare myself. I guess I should show y'all what abstract algebra is. Oh my goodness, I'm nervous. Actually nervous. Mainly because the computer is so hard to work with. I don't want to mess it up. I don't have enough USB ports for everything. Let me move the mic a bit closer. Alright, so I'm going to be doing 14 chapters. Yeah. So chapter 1, today I'm going to try to do chapter 1, 2, and 3, which chapter 1's about just basic mappings and operations. Chapter 2 is introduction to groups, so just the basic groups. And then chapter 3 is some number theory stuff that's required for abstract algebra. Then chapter 4 we actually get into the deep group theory. So that's what I'm going to be doing tomorrow is group theory. Then that's also, and then chapter 5 is about homomorphisms. 6 and 7 are, 6 is an introduction to rings, and then 7 and 8 are about like stuff you can do with rings and fields. Mainly you've got complex numbers, real numbers, and polynomials. Then chapter 9, oh no, it's almost 10:45. Chapter 9 is about quotient rings. Chapter 10 is field extensions. Chapter 11 is Galois theory. It's not super in-depth, but it does go through the undergradness of it. And then chapter 12 is geometric constructions. Then we've got chapter 13, which is more applications, and then chapter 14 is symmetry, and then that's it. So if y'all want to see, that's so I'm only doing this today, the first 13 sections, which is actually quite a lot because there's a decent number of problems per section. Okay, I wish I could see chat, but I really can't. I might be able to. All right, it's 10:45. Gotta start. So let's get to this. Oh, let me exit Twitter. And yeah, let me scroll up to here. All right, abstract algebra speedrun. I don't know how I'm gonna do this. I don't know if y'all are gonna like it, but let's do this. All right, 3, 2, 1. All right, we're off. Well, my commentary is gonna be a bit because I'm actually learning it. I don't know everything about it. So all right, I will be quiet for a little bit, but basically it's talking about mappings, functions, and it says read the appendices for like helpful stuff about someone said stuff in chat. Okay, let me move this over here. Oh my goodness. It's so stressful seeing. Okay, let me move this over here. Hello. There we go. All right. So stressful seeing that time because I'm trying to time it, but like the minutes and stuff really don't matter. Alright, so the appendices, alright, we know this. Mappings are important. Alright, what is the definition of a mapping? It is a mapping from a set S to T. It's a relationship that assigns each element of S to a uniquely determined element of T. S is the domain, and T is codomain. Alright. So that's just the mapping. And we've got some kind of rule. And it's unique. So it's not just a relation. Alright. And now it's giving some notation for mappings. It says in this book it'll be typically with Greek letters. So we've got some examples. I might just skip to the problems. No, I'm not. I'm just going to look at these examples and see if there's anything new here. Yup. AX, 2A of Y, yeah. That's the mapping. That's another mapping. But that is not a mapping because it's not unique. Not everything gets assigned. And also X wasn't uniquely defined. I was looking at this one right here, if you can see. So this is kind of important. Two mappings. I guess they say alpha and beta. I'm going to use F and G. F and G are equal if and only if domain A equals A, or I guess I should say domain are equal and codomain are equal, and f of A equals g of A for all A in A. What's up, Lily S? So f of A equals g of A for all A in A. That is, if you can't see the problems I'm doing, that is a good point. I'm going to try to figure that out right now. I tried figuring it out earlier, and I noticed that y'all can't see anything. So how about this? I do problems. So I have my notes on this, and I'm going to do all the problems on a whiteboard. So give me a second. And my battery's already running low. Okay. So things didn't go as planned, but we work with this. So step 1 of problem solving is setting up the stream. Okay. Yes, I know this is not professionally set up, because I'm not a professional. We're not even a professional. I haven't done this ever before. So, yeah. So, first off, we do that. Then, we do this. Remove this to, like, I don't know. None. Okay, we're going to move this, move that. Giving up now. Once it is all set up, things will be good. So I won't be able to see chat unless I look behind me. But this is the only way in order to have the plug be able to reach the outlet. And we can put the camera up here. Okay. Alright. I don't even know how this looks. I'm just trying to keep my computer alive. Oh my goodness, it's a mess. This is probably the fun part to watch. All me messing up on all this. But just because we mess up doesn't mean it's the end. And in fact, it is not the end. For we have conquered the dead laptop. Alright. over here. So I will be doing all the problems on there, but right now I'm taking notes on the chapter. Alright, so let's just see if things look good. They look alright. You're taking linear algebra? Well, you might be able to understand quite a bit of what I do in here. Linear algebra is basically just applied abstract algebra, so yeah, you should be able to understand. Alright, can y'all see? You can't really see my notes, so I'm going to switch this here, and the microphone's in the way, so I'm going to move that to here. And then no data. What does that mean? How about this? I just put the webcam on the microphone. Isn't that big brain? That is some serious big brain moves. Alright, let's see how that looks. Yeah, check OBS. Yeah, that looks alright. Alright. Okay, so now we can get back to our thing after that little thing with the computer. So yeah, right now I'm taking notes on the chapter, you know, just writing down definitions, talking about quantifiers, and also I do the examples. So the identity mapping, they denote iota. I'm just going to do lowercase our ID of x equals x for all x in S. That's important to make sure that S is a category, or sets are category, is a the set of sets is a category, or the category of sets. You know what? Don't worry about that. All right. The rule. Okay. So the rule this, I need to write this down. ST mapping to S plus T defines a mapping of ordered pairs. I know y'all can't really see this, but I'm trying my best. All right. And ST does not equal TS unless T equals S. All right. So the image is that the set alpha of A is called the image. Our alpha of A is the image. I guess, I mean, I normally use the IM of F, but yeah, that's the image. It's a subset of the codomain. It's a subset of the codomain T. So, on to, or surjective, when image equals codomain. And to show that two sets are equal, you have to prove that each is a subset of the other. And then one-to-one, or injective, if, let's see, we've got, oh yeah, f of x1 equals f of x2, right? No, does not equal. If x1 does not equal x2, x1, x2 are in S. Basically, everything has a unique thing that came from. and it's bijective if both injective and surjective. So yeah, I'm just taking notes on the chapter. I'm not doing problems yet. When I do problems, y'all will see it. All right. And a distinction about finite sets. If what is it? You can map everything to. Wait, hold on. Okay, yeah. There's an injection, but not surjective. Wait, no, that's infinite. Hold on. Let me make sure I get this definition. Basically, if there's a mapping to a subset of the real numbers, then it is finite. If there is a one-to-one mapping or a bijection between the entirety of the natural numbers and what is it? The function, then it is or the set, then it is countably infinite. And if there does not exist one, then it is uncountably infinite. Okay, problems time. So those are my notes for the chapter. This section. Let's do some problems. I know y'all can't see the problems I'm doing, so I'm gonna go ahead and copy them, mostly verbatim, because some of them are like really long paragraphs that can be solved really quickly. Where's my eraser? There it is. You're gonna be with me? Hey, can y'all hear me? Change the camera angle. I currently can't because, okay, I can't change this one because I need my computer to charge. I can change this one. Let me make sure this is good. Okay, so let's try to get a camera angle such that we can see the whole board. That's not the whole board. Maybe go up here. A bit louder. I can change that too. Give me a second. I'm basically being limited by the chords. Okay. Let me move the book in my lap. Y'all see that? It's not that good, but it's like the best I can do. Okay. I can get a bit louder. Oh my goodness. Okay, I'm gonna get louder. Get a thing. That would be nice. That would be nice. But I don't have the thing, so I would need some kind of like extender. Alright, so let's go ahead and go to sounds, recording devices. I use some Aquafina. It's pretty decent. Okay. Can y'all hear me? Yes, y'all can. I know y'all can. But where is it recording from? Okay. How does that sound? It probably sounds the same. And then let's go to properties. It's really quiet. Levels. How does this sound? How does this sound? Wait, oh, I haven't applied it yet. It's the same. Yeah, hold on. Give me a second. Now it sounds better. No, it doesn't. Hello? Hello, 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 hello. Does it sound better? Much better. Yep. All right. We are back in business. Yeah, don't worry too much about time. It's going to take a long time. Hands are like corpses. I didn't know that. All right, let's see how we can... I think I'm just going to read out the problem just because some of these are just really long, and then I will write down necessary information to actually solve the problem. Where can I put this? Right here? Okay, I want y'all to be able to see the board, but I want to... Oh, big brain. Big brain. All right. So S... Am I writing big enough? Might need to write bigger. I'm going to write bigger. Okay, no, that's not big brain. Dude. This is totally not optimal. S equals the set W, X, Y, Z. And T equals the set 1, 2, 3, 4. Define alpha from S to T and beta from S to T by just shout. You know what? I might. I'm also just not speaking directly into the microphone. I'm speaking this way, and the microphone's to my left. So, I'm speaking straight forward and not to the left. By alpha. Okay, this is gonna be a big slew of definitions. Alpha of W equals 2. Okay. Alpha of W equals 2. Alpha of X equals 4. Alpha of Y equals 1. Alpha of Z equals 2. Beta of X equals 2. Beta of Y... I need to move some stuff. I'll try to keep that there. Move that over here. There we go. Beta of Y equals 3. And beta of Z equals 1. Let's see how that looks. Oh, the mic's in the way. Let's move the mic up here. I guess. Hold on, let me try doing that. Let's put this up here. Okay, and let's angle it like this. And that doesn't help. And I really don't know where to put the mic because it can't reach much further. It can't reach much further, so straw on my microphone. We're gonna find a good place for this microphone. If it's the last thing I do, which I hope not, but we're gonna find a good place. Basically we need it. Okay, we can do that. We can do that, then we can do like that. Ha ha ha! We could do like that. Oh, that's not good. That's not gonna stay, is it? Let's tighten this up. All right. Like that. Okay. How well can y'all hear me? Can y'all hear me when I'm talking this way? Hello? Can y'all hear me when I'm talking this way? No? Well, this is like the best I can get such that y'all can see what I'm writing. Beta of z equals 1. Let's get this thing. Okay. Beta of z equals 1. Alright, A. So question A is alpha, beta, surjective or bijective, whatever, each of them. So part I is alpha bijective or injective. Well, let's see. Alpha of W is 2. Alpha of X is 4. Alpha of Y is 1. Alpha of Z is 2. So, not injective. And also, 3 doesn't get mapped. So, not bijective. Or, surjective. Because what is it? 3 doesn't get mapped. Like the image of alpha doesn't get mapped, or doesn't equal the codomain. Alright, now time for beta. Beta of X is 2. Beta of Y is 3. Beta of Z is 1. What is beta of W? 4. So it is bijective because 2, 3, 1, and 4, everything gets mapped and everything has a unique mapping. So it is bijective. Alright. Next part, B. So this is all question 1, by the way. We're barely on our first question. 20 minutes in. Alright, let A equal WY and B my eyeliner. I think it's just my hair and the lighting. Beta of, or let A equal that and B equal X, Y, Z. Determine each of the following. Alpha of A, alpha of B. Oh my god. Why are these questions so long? alpha of A is what is it? It's the set of things that are mapped from, so W and Y. So alpha of W we saw was 2, and alpha of Y is 1. Okay, now alpha of B oh no, we were finding beta of B. Okay. Which will be, we got x, y, z. So x was 2, y was 3, and z was 1. Alpha of A intersect B. So A intersect B equals just y. So alpha of A intersect B equals where is it? 1, set 1. And then alpha or A union B just equals W x y z. So alpha of that, or beta of that, is just simply I don't think order matters, but if it does, it's going to be beta 4, beta x 2, beta y 3, 1. And that's the answer, beta of B. Alright, or A union B. Alright, and that's the answers. So, do I watch Attack on Titan? Yes, I do. I want to watch that episode on Sunday. So that was problem 1. Hopefully y'all see what I did. But I am voicing my work, so hopefully y'all can hear what I'm working out. All right, next question. So alpha of n equals 2n beta of, if you're wondering why things are in Greek letters and not like normal letters, I don't know. I really don't know. That's just how this author does things. And then gamma of n equals n cubed. Normally this would be like F, G, and H. This means the same thing. And then n is in Z. Okay. Which of the following 3 mappings are onto? Oh. Onto, meaning that the codomain, the things that get mapped to, and which ones are 1-to-1. I think they're all bijective. I mean, I would want to prove them, but actually no, it doesn't say prove. Yeah. By the way, unless a problem specifically states prove, I'm not going to prove. I'm not going to prove my answers, because proving takes sure. Alright. So we've got alpha of n equals 2n. So I guess I could do, not really proof by graph, but like basically the graph of this one is going to look like this. 1-to-1 basically means the horizontal line test. And surjective basically means that its range is the same as the whole thing. Oh, I just realized though, this is So none of these are one-to-one. So this would be true if it was a real number graph, but it's not. It's a sequence graph because it's only with integers. So it like this. So in that case, not every integer gets mapped, at least for alpha. For beta, it does. So beta is bijective. Alpha is not one to. It is one to one. Is injective, but not surjective. And then gamma, same deal with that. Looks like that. So gamma is injective, not surjective. Okay, can y'all see that? What do I think of season 4? I think it's pretty cool. We get to follow different characters, and it's going to be really cool seeing them meet up. It's really cool seeing the other perspective, and and I also think like the action's pretty alright. Still doesn't capture the same magic as the first season, but it's fine. Like, I don't mind. It's still fun. It's still awesome to watch. Alright. Oh, that was just part A. Or no, part B, A and B. Alpha of n, beta of n. Don't need to do that. Alright. Third question. So S equals X, Y, Z. T equals 1, 2, 3. We have those. There are 27 mappings. Okay. How many mappings are there from S onto T? So how many onto mappings are there? And I want to say it's 6. But I should probably show that. So that's 1.3. Let's just show. So we can have 1. That's one mapping. You can have this one. Yeah, it's like the permutations, basically. And then you can flip them around. So yeah, it's 6. Basically our order of S factorial. Or it could just be order of S, or not order, magnitude. No, I forget the word. Didn't mention it in here. Because it's just cycling. So how many one-to-one mappings? Oh, I just realized that was one-to-one mappings. For onto, it just means that each thing gets mapped to. And we know that there are 27 mappings. Hold on, let me actually work through this. Because I didn't actually work through that question. I think it'll help to draw a picture. So we have X, Y, Z. Obviously this isn't a proof, but it doesn't ask to prove. We don't have proofs until later on in this section. So so we want onto mappings. Well, since the magnitudes are the same, they're going to basically be one-to-one because they have to be functions, right? You can have this, that, this. So it's basically, there's only there's the one where X, I'm going to define this by alpha. Alpha of X equals 1. There's one alpha, then alpha, there's 4 here. No, 2. There's going to be 2 more here. So there's 2 mappings. When alpha of y equals 1, there's two mappings. Alpha of z equals 1. It's basically the factorial. No. Not alpha of z. Alpha of x equals 2. There's two mappings. Alpha of y, or alpha of x equals 3. There's two mappings. So we add them all up, and then we get 6. Okay. So that wasn't an actual proof, but it was just more just showing how I got that answer. How many one-to-one mappings? So we know that there are 20 mappings total, 27 mappings total. How many one-to-one mappings? Well, let's see. Oh no, my brain is already dead. The opening? I think the opening's pretty good. It's not my favorite, but I still think song is eh. The visuals are pretty cool. And yeah. Okay, so my brain is already dead after 4 problems. That is not good because we have 1,000 more to go. It's because I'm hot. I need to take off this jacket because it is boiling in here. Okay. We can do this. I'm just gonna need some coffee and food. Okay. How many one-to-one mappings are there from XYZ to one, two, three. So I think I counted these wrong. No, I didn't. No, I didn't. That's right. This one's also 6. It's the same deal here. And the reason I say I didn't count these wrong is because my method here was the same as you'd use for this. It's just that the reason I didn't count differently was because if you had 2 things from here mapped to the same thing, oh wait, then it wouldn't be surjective, basically. It wouldn't be surjective if you had x and y mapped to 1. For here though, you do use this method right here. So this one's also 6. All right, 1.5. How many mappings are there from S onto 1, 2? Okay, so this one's different. This one will be different. So let me draw a better picture. We have X, Y, Z, 1, 2. So in this case, some things are going to have to. So we have this, that. That's 1 mapping. We have this, that. That's 2 mappings. This would go here. We have 2. Obviously, if you were proving this, you'd have to prove that the ones that you counted are them all. And there's special ways to do that. 1. That's 3. And then we have 2 here, and then we have,
and then you just switch them around. So you multiply everything by 2. It's also 6. So we are at 18 mappings. We need 9 more. On 2, there's none. So for 6, there's none. 0. All right, and then we're done. Okay. Basically, if the orders are different, then, or if the cardinalities are different, then the relativity stuff, kind of. I'm kind of hungry though. I think I'm gonna order some food. Okay, so now we're on question 7. Making progress. So alpha goes from S to T, and beta goes from S to T. Okay. So now I just have to complete the statements. Okay, that's easy. Alpha is not on 2. Or injective, or no, on 2 is surjective. If and only if for some for some, I don't know, A in S, alpha of A is not in T. That makes sense. Oh, I put alpha of alpha at 1.8. Alpha is not injective if and only if alpha of x1 equals alpha of x2 and x1 equals or does not equal x2. x1, x2 in S. Okay. 1.9. Alpha not equal B if and only if what is it? Since their domains and codomains are the same, it's only the only thing that would make this not true if only if alpha of x does not equal or exist, I guess. If there exists an x in S such that alpha of x does not equal beta of x. There we go. So that's the answer for that. So now 1.10. Beta is bijective if and only if for all y in T, beta, or I guess inverse beta exists. I mean, you'd have to prove that the inverse it only exists if it's bijective. If for all y and t, beta of x equals y, beta of x equals y for some. Or I guess you could also say beta inverse of y is an s. I've proved that somewhere else, but it didn't say that in the book, so y is in s. Okay. All right. I think that's good enough. Not sure what we doing. We're solving math problems. That's all you gotta know. We're solving math problems. Just very abstract math problems. All right. So for each of the mappings, I have to say if they're on one injective. So for the following, state if injective, surjective, and describe, what is P? Describe f of r plus. Right? Can y'all see that? All right. And just so y'all know, I do not know the abstract algebra already. I am learning it like as I go through this speed run. I'm just trying to learn it within 2 weeks, which is a very, very tall order. We're already an hour in, aren't we? Yeah. Don't worry, we're getting places. All right. Describe f of r plus. All right, so first off, we have 1.11, f of x equals 2x. Since we don't have to prove anything yet, I can just do a proof by graph, I guess, where you have, this is the graph. Would you look at that? It's 1 to 1 because it satisfies horizontal line test. And since the range isn't the best word, image equals the whole y-axis, it's it is surjective. So now let's do 1.12. F of x equals x minus 4. Again, proof by picture, even though that's not a valid proof. It gets the idea across because it doesn't say prove anything, at least not yet. The proofs are later in the problem set. Again, it's a line. Everything gets mapped to a real number on the y-axis, and satisfies horizontal line test. So it is bijective. 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 And then I guess if it wanted me to describe f of the positive, it would just look like this. It would just look like this. Positive axis. Alright, next one is f of x equals x cubed. Oh wait, that's not the graph. Boom. Boom. Yep, this speed run is gonna take probably a long time. I'm not gonna be awake for the whole thing. Obviously, I'm gonna need to sleep. But yeah, this is gonna take a while. Okay, so we've got f of x equals x cubed. No worries there. Again, horizontal line test, and everything in y gets mapped to this. I don't need to prove it, I just need to state it and show some reasoning. If I were to prove it, it would take a lot longer. Oh, that was... Did I skip 1 point? Oh, I did 1.12 twice. 1.14. F of x. Okay, so this one, x squared plus x, it looks something like this. What is that? X plus 1. Yeah, it looks something like this. That is not one onto, because these don't get mapped. But it is not 1-to-1. So neither surjective nor bijective. Okay. See if I can get through the first part of the problem set before the hour mark. Oh jeez. Don't want to mess up the book. Alright. Okay. So 1.15, do the same thing for f of x equals e to the x. So it does satisfy the horizontal line test, but it does not satisfy, it's not everything on here gets mapped to. So injective, not surjective. And then 16 for f of x equals tan x. It's going to be the other way around, because tan x looks like this. Oh no, it doesn't look like that. Looks like this. And then you have an asymptote here, and it goes like this again. So, does not satisfy horizontal line test, but it is surjective. So, not injective, but it is surjective. Alright. Because everything gets mapped to some unique number on the y-axis, is what surjective means. Well, in the case of reals to reals. Yeah, I don't have school for the next couple weeks, so that's why I have time. I do have some things I might need to go to, but yeah. Alright, A is the set of odd numbers. I guess I could do equals the set 2n plus 1 from n equals 1 to infinity. V equals the set of even numbers. So, oh wait, what am I doing? I guess I don't really know how to state it, but it's like A equals set x stat x is congruent to 1 mod 2. And then B is a set x such that x is congruent to 0 mod 2. And C is a set X such that X is congruent to 0 mod 4. So those are our sets. I'll see that. I'm going to try that here. Okay. With example 1.10, with alpha as in example 1.10. Oh, example, not problem. Oh boy, I'm like really hungry. At the 1 hour mark, I'm ordering food. Alpha of A, so alpha of n equals 2n. Hold on, give me a second. I am ordering food. I'm gonna go ahead and pause. I'm gonna go get food. I'm like really hungry. I'm at least gonna order food. I'm not sure if I'm gonna get food. So let's go ahead and pause. How do I do that? I actually don't know. What is it? F5. Okay. Alright, so I will be back in about 30? Give me like 15 minutes. I'm back. Busy. I'm busy. Yes. All right. I'm back. Hello. So, while I eat, I'm going to go ahead and read through the next chapter. Or not chapter, section. Let's put this. So the next. All right. All right. I'm going to read the next section. I know there's not many people watching anymore because they left, but it's fine. So let's go ahead and hit go on here. And while I eat, which, yeah, that's what I'm doing right now, eating. Also can read. Yes, I know it's quiet, but I'm back. Hello. Hello, people. I'm eating lunch. So definition of composition. We've got beta after alpha of x. Like that. Okay. Alright, so the theorems and proofs. So we have theorem. Alpha is a mapping S to T, and beta is a mapping T to U. If alpha and beta are onto, then the composition is onto B. So I know y'all can't see what I'm writing. I guess I can write on this side. But I'm basically just taking notes on this second section. If so, it's an if and only if. No, it's not. Beta after alpha is onto, then you only know for sure that beta is onto, so it's not an if and only if. If alpha and beta are 1 to 1, then the composition beta after alpha is injective. if the composition is injective, then we only know that alpha would be injective. So I'm going to go ahead and write down these proofs, read through them, I guess, because that was a theorem. But before I do that, I'm going to read through them while I eat. So let's get comfy here. And by the way, if you're getting comfy, if you're watching this, go ahead and get comfy because we're going to be in here for the long haul. This is going to be a very long thing, so I'm not sure how I'm going to make this entertaining because it's really boring. Best I can do is say do random stuff. I think the most entertaining part was me setting up my setup. Oh, this is good. Oh wow, I already have 21 likes. It's impressive. Just me eating McDonald's. Hello people. I am currently reading my textbook while eating because I was really hungry. So I'm just chilling, reading. So if B composed of A equals identity ID S and alpha composed with beta equals ID T, Then the mapping is invertible and has an inverse. Okay. And the theorem, they don't prove it, but there is a way to prove it. A mapping is invertible if and only if onto bijective. All right. So oh yeah, we chillin'. This is so amazing. I love this, even though no one's here with me. Well, there are people here in spirit, but realistically, no one's gonna watch this. It's just sort of here for proving that I have done it. Okay, I need to quickly check how to change split. Okay, numpad 1. Okay. So I think I'm gonna split here because I guess I didn't do enough proofs, but I have already done like a lot of these proofs in this first section in my set theory book. I mean, it's not that I shouldn't do them. I probably will. But it's just that they're only there just to make sure that you're good at like set theory stuff. So I'm gonna go ahead and split here and just move on to the next section. Oh, did I do any? Yeah. Okay. And now it's proving that, yeah, that theorem. Okay, I'm still eating though, so I need to quickly, or not really quickly, but keep eating. I already read this section though, so let's look at these problems. We've got blah blah blah. Also determine the image. Okay. Our first proof. We're gonna be seeing a lot of those in abstract algebra. Is 2.7. So look forward to that. Get to see me actually prove stuff. Let me eat, guys. I'm just saying, let me eat. Don't judge me. Yes, I'm busy.
Can I come in?
No.
I have your pills, and I'm putting a salt pill in there, so you need to make sure you drink lots of water with it.
Okay.
Do you want me to just leave them downstairs?
Yes. Okay. So prove that if alpha goes from there equal alpha. When I prove that. Yeah, that's how I prove it. Okay. Never mind. I know how to do that. Ugh. Oh, there's one more nugget. That's always amazing. When you think you were done, but you weren't. Alright. Let's get back to work. It took me about 16 minutes to eat. Sounds about right. Okay. So, I did skip a lot of problems in that first section. And that was because I've already done quite a few of those. I mean, I can go back and do some if y'all really want me to. But that's not really the abstract algebra. The point of those problems is just simply to make sure that you're comfortable with sets. Also, I guess I just did a mukbang. So, that's nice. Okay. Alright. So let's get the board back out. Put this over here. Put this over here. Where'd my marker go? I know I'm not talking loud enough, but... Oh boy. Oh, there's my marker. Here it is. Alright. Let's get to work. Let's get to work. Alright. Alright. So, alpha of n equals 2n. Beta of n equals n plus 1, gamma of n equals n squared. Alright, so now 2.1, alpha composed with alpha equals 2n, or I guess 2 times 2n equals 4n. Alright, 2.2, gamma after alpha n, I guess, is going to be gamma of 2n equals 4n squared. 3, alpha after beta of n equals alpha of beta of n, which is n plus 1, which equals 2 times n plus 1. 2.4, beta of beta is going to be n plus 2. 2.5, beta after gamma of n is going to be beta of n squared equals n squared plus 1, and then gamma after gamma equals gamma after gamma equals n to the 4, basically. It's going to be gamma of n squared equals n to the 4. Right, okay. Seems pretty good on our composition. Pretty good. So now our first proof. Prove that if alpha maps from S to T and alpha, then alpha composed of identity IDS equals alpha, and IDT composed with alpha equals alpha. So to show that two things are equal, we first have to show that so prove. Show that two things are equal. We first have to show that their domains and codomains are the same. So how do we show that? Well, alpha maps from S to T. IDS maps from S to S. So alpha of that is going to map from S to alpha after IDS maps from S to T. Because we end at S, and then we go after S, we go to T. Is that a valid proof? Sort of. That's just a good way of showing it. And then so this is part I. We're showing that ID alpha composed with IDS equals alpha. So next thing, we pick we basically have to show that let n be in S, or I don't like writing S's, so I'm just going to let n, or X, A. Let's use A. A be in S, okay? By definition, IDS of A equals A, right? So alpha after IDS of A equals alpha of IDS of A equals alpha of A, since A was arbitrary, alpha after IDS equals alpha for all A and S. Okay, so that was part 1. Part 2, you have to show that IDT after IDT after alpha equals alpha. So let's see how the domains and codomains match. So alpha maps from S to T. IDT maps from T to T. So therefore, IDT after, I say after because it helps me like discern what it's talking about. After alpha of I'm going to call it lowercase t. Oh, wait, no, why am I calling it? I haven't defined it yet. Is going to map from S to T. So we've shown the first condition that the domains and codomains are the same. Because basically what happens is, just by definition, S will go from T, and then we apply IDT, it'll go from T to T. So the composition goes from S to T. Alright. So now let T be in big T. Wonder if y'all can see this. It's sideways. Okay, yeah. Let's try doing it like this, because I know reading sideways is tough. Let T be in T. Okay. By definition, ID. Oh wait, no. I don't need to let T be in T. Okay, hold up. I have to do this a little differently. IDS S to T. So actually what we're going to do is let A be in S. So alpha of A is in T. So by definition, IDT of T equals T, where T is in big T. So IDT composed with alpha of A equals IDT of T, where T equals alpha. Oh wait, no, I don't even need T. I just need to say that it's okay, I know what I say. Alpha of A, since alpha of A is in T, IDT of alpha of A equals alpha of A, since A was arbitrary. I'm gonna get rid of that step whenever from now on the A is arbitrary, because it makes sense. Since A was arbitrary, what is it? IDT of alpha equals alpha for all T, for all A in S. And that's the proof. Bit long-winded. Okay. From example 2.1. inverse of beta? Oh. Yeah. I mean, I did that in my head, but I don't really need to do that. Write it down. It's just, it makes sense. It's pretty obvious. So, that was 2.7. How many problems have we done? I don't know. The goal is learning abstract algebra, not doing as many problems as possible. Alright. So, this one's just finding the inverse. And since we're dealing with F mapping from R to R, we can just do, since R is a field, we can do all the stuff. We can divide. So we'll see more about fields later on. But basically, division is defined in fields. All sorts of stuff is defined in fields. So now we can just do, alright, 2.9, f of x. So we're just finding inverses equals 5x. So we're just finding it. So x equals 5 times g of x. So g of x, which is the inverse of f, equals x over 5. We can do that since R is a field. That was part A. Part B, do the same thing for f of x equals x minus 4. So what we do is we replace f of x with x, and we have g of x. So this is just standard algebra. So g of x equals x plus 4. F of x equals 10 to the x. Now we have x equals 10 to the g of x. You can take the log of both sides, and we get g of x equals log x. Okay, and that's it. 2.10. Alright. 2.10, we have a f of x equals minus x over 2. This is kind of boring, but I want to do some of those later proofs. So I guess g of x equals f inverse, which is going to be minus 2x. B. So g of x equals cube root of x. And then f of x, or c, equals ln x. So g of x equals e to the x, where x is bigger than 0, where x is a member of R plus. Okay. That was pretty simple. Okay, so next, state the decide if it's sufficient condition. So this is kind of like a true or false. I'm not going to write down everything. I'm just going to go through it. A is invertible if, or alpha is invertible if alpha is 1 to 1. False. Wait, oh no. No, that's false. Alpha is invertible if only if alpha is 1 to 1. Still false. It's not sufficient. A necessary condition for alpha to be invertible is that it be 1 to 1. True. A sufficient condition for alpha to be invertible is that it is 1 to 1. False. For a mapping alpha, decide whether or not following is true. Alpha is invertible only if alpha is on 2. False. Alpha is invertible if alpha is on 2. False. Sufficient. False. Necessary. True. Okay. What did matrix stuff say? Alright. Now we're on 2.13. Okay, this is an interesting problem. Or it's not that interesting, but not boring, basically. So we have f, or their mappings from R to R. F of x equals sine x, and g of x equals 2x. So f of g equals sine of 2x. G of f equals 2 sine x. So f of g does not equal g of f. So composition, it's just an example of composition is not commutative or abelian. Alright. Which of the following are invertible from R to R? Sine, cosine, tangent. I'm pretty sure. What is it? Arctan exists for anything. Inverse sine, so I think it's only arctangent. Yeah. Or it's only tangent, because that one is... Oh wait, no, none of them. Sorry. Sine looks like this, right? So it doesn't extend over here. And it also fails the horizontal line test. Same thing with cosine. Tangent looks like this, right? It fails horizontal line test, so it's not invertible. Okay. Complete the following statement. A mapping alpha from S to T is not invertible if alpha is not 1 to 1 or alpha is not surjective. Okay. I know I'm not talking loud enough, but yeah. Okay. Another complete the following statement. I did that in my head. Okay. So we're going to skip down a bit because the other ones are just writing statements and I don't want to waste ink on my marker to just write out a statement. So let's go with oh yeah, I'm not talking the right way, but let's go with, we're going to start with, that one is using an example. I'll just do it in my head with example 10. Wait, hold on. Example 1.10. I have to go back. Yeah. Okay. Proof. So, prove that the inverse of an invertible mapping is invertible. Invertible. Yeah. I'm gonna quickly check Discord real quick. I should have done that while I was getting food, but yeah. Oh boy. To get off my phone now. Alright. Prove that the inverse of an invertible mapping is invertible. So we have to prove this. Let me make sure that my proof is good, but I'm going to do some scratch work really quick just to see how I should organize my proof. So we have F and F inverse. F maps from, I like doing A to B, they like doing S to T, it doesn't really matter. F inverse maps from B to A. So we have to prove that if it's invertible if it's bijection. That's one thing to do. So yeah, I guess that's one thing the way to prove it would be to show that F inverse is bijective. Show F inverse is bijective. So I guess that's the easiest way to do it. Because we already had the theorem from earlier. So, all right, proof. So to show it's bijective, first off, we got to show that it's 1-to-1. Well, first off, we know F is 1-to-1. So how do we prove that F inverse is 1-to-1? Oh no, I'm already getting tired because of the food. Need to drink some water real quick while I think about this proof. So the way I like to prove things is just write stuff down and see where that leads me. It might not look pretty, but that's how I like to prove stuff. So let's just show that it's surjective. To show that it's show surjection, pick so we have to show that everything in A gets mapped to by F inverse. So we know, so let X be in A, or no, yeah, so we have to find something such that X be in A. We have to find something such that F of it will equal X, or F inverse of it, which is just F of X. F inverse of F of X equals X. So, and since F of X is in B, then then F inverse is surjective. Okay, yeah. That wasn't too bad. Now show one-to-oneness. I need to pick, I guess showing the opposite. Let y1 be not equal to y2. Or I guess I could pick y1 and y2 and show that f inverse of them equals the same thing. y1 and y2 be in B. And I guess I'll show injection. We chillin'. I know I'm taking forever on this one problem. It's already 1:40. 1 hour and 40 minutes. Okay. I mean, we're almost done with the section. y1, y2, B and B. So, y1 and y2 are in B. Oh, yeah. So we need to show that f inverse of y1 equals f inverse of y2. So f inverse y equals something equals some x, which is in A or y1. So we could apply f to both sides. So y1 equals f of x. And then same thing with y2. F inverse of y2 equals x1. Wait, what am I doing? What am I doing? This proof is not right. Well, this part of the proof. The other part was fine. I'm just gonna assume that y1 does not equal y2. Okay, and then y1, y2 are in B. Okay, so we assume that y1 does not equal y2. So therefore f of y1 equals some x1 in x1 in x1 in A, applying, or this is f inverse, applying f to both sides, we get ID B of y equals f of x1. So y equals, or y1 equals f of x1. Okay, next step will be so now we have f of, assume that they go to the same thing, basically. Assume that they go to the same x, basically. And we apply f inverse to both sides, and then or f to both sides, we have idb y2 equals f of x. So y2 equals f of x. Contradiction. Thus, f of y1 does not equal f y2 when y1 doesn't equal y2. Thus, bijective, thus invertible. There we go. That's the proof. What's up with the back camera? Well, originally it was right here. It was supposed to be right next to me, but I have to charge my computer, and the only outlet that's close enough is way back over there. So I have to. Can y'all see that proof? Yeah, I guess y'all can. Okay. Next question. Or I guess next one that we want to do. Prove. Okay. Let me take the water. Okay, prove that. Prove. And no, we're not on problem 223. We're on problem 2.23. Prove that if alpha maps from S to T and T and beta maps from T to U, and gamma, prove that if and gamma maps from T to U is onto, or alpha is onto beta composed of alpha, beta composed with alpha equals gamma composed with alpha, then beta equals gamma. So we need to show, so we already know by their definitions that their domains and codomains are the same. So all we need to show that they map to the same thing. And we know, so proof. We know beta composed of alpha of just some A equals gamma composed of alpha of A for some A in S. It's onto, so that means alpha of A has to be, since alpha is onto, alpha of A is in T. So this will be this will be beta. Let T equal alpha of A. Beta of alpha of A equals gamma of alpha of A equals beta of T equals gamma of t for all t in S, since it was on 2 basically. And that basically completes the proof. Yeah. Thus beta equals gamma. Okay. That was pretty simple. Alright. Next question is literally the same thing, just a different sign. 1 to 1. Oh no, it's not literally the same thing. Okay, that's actually kind of interesting. That is interesting. Okay, so it's like the same type of question, but quite a bit different. It looks the same. Prove that if beta maps from S to T, gamma maps from S to T, alpha maps from T to U, alpha is injective, then and alpha composed of beta equals alpha composed of gamma. So we know that. That's our definition. We're trying to prove then that beta equals gamma. So first off, their domains and codomains are the same. So don't need to prove that. Well, we only need to prove that. So we know, start off with what you know. We know that alpha composed of beta equals alpha composed of gamma. I'm gonna do of let's see, what is it? S. Let's just do A, where A is in S. Okay. So what can we use with this? We know that alpha is 1 to 1. We don't know anything about beta. But what would this mean? Well, and we're trying to prove that beta of some element is the same thing as gamma of some element. So that means that, so we know that alpha of beta of A, which is in U. Okay, so these are both in U, alpha of beta of A and alpha of gamma of A, and they're equal. So they're the same for all A. So I guess I need to put this for all here. Okay. I think this will be our last problem actually for this section. There's a couple more that are more just give examples of certain things that I can do in my head. Okay. So, we need to prove. So for all A and S, this is true. So now we know that alpha is 1 to 1. So that means alpha of some element. That means alpha of some element t will always get mapped to exactly one element. Alpha will equal u, where t is in T and is unique, and U is in U, big U, so this is lowercase u and that's big U, and is unique. So I guess I could do a proof by contradiction here. Assume that, well, since alpha of beta of A, I guess since let T1 equal beta of A and T2 equal gamma of A. Yeah. Oh my goodness, y'all can't see this point. Y'all think I'm on well, I know y'all probably don't think, but people might join the stream and think I'm already on problem 224 when I'm really on problem I think I've done around 40 problems, maybe 50. Still a lot, but a lot of them were really easy, so this one's an actual proof, and I'm trying to work through it. I have spent a decent chunk of time on this, but this is our last problem for this section. So T1 equals beta of A, T2 equals gamma of A. Since, I guess, alpha of T1 equals alpha of T2 equals some unique element U in U, then T1 equals T2 since alpha is 1 to 1, thus beta of A equals gamma of A for all A in S, thus I guess that's the same thing, beta equals gamma. Okay, that's the proof. And I didn't need to show the other condition because it was already stated. Or basically already stated. I mean, there's like a little technicality to it, but not really. Yeah, just straight definition. Okay, last one of this section. So now I guess I can read a new section. So I'm going to put this down and read the next section. Let's go ahead and split. All right. Operations. All right, definition. My pen already dead? Gotta use a new pen. Is this pen already dead? Okay. An operation on a set S is a relationship that assigns to each ordered pair of elements of S a uniquely determined element of S. Okay. So, thus an operation is just a special kind of mapping that maps star basically maps from the Cartesian product of S to S. Okay. So like addition maps from A and B to A plus B. Okay. So now, how do we prove closure? Oh, wait. So in order to be an operation, it must be closed. Like it must be closed to be considered an operation. All right. That's just another example. That's composition. Basically proving that composition is an operation. What is this? S is a finite set. Specify S means... Okay. So it's basically showing tables that we can define the operation. It's like a multiplication table. And it's called a Cayley table. Okay, so I guess we'll be using that later. Called a Cayley table. Okay. An operation is associative if, so associative if A star B star C equals A star B star C for all A, B, C in S. And why did I have to use S? My S's all look like 5s. Okay. So next, an element E in a set S is an identity if, so identity, if E is identity if A star E equals E star A equals A for all A in S. And inverse. If A star B equals B star A equals E, B is inverse of A, and then commutativity. If A star B equals B star A for all AB in S. Okay. Alright, so I know there's not much problem solving going on right now, but hey. So there's a example. So now it defines a general linear group. So GLN of some field F is a set of matrices with elements with a non-zero determinant. Non-zero determinant, and what is it? Non-zero determinant and it's not defining that. It's just that I'm just sort of writing it down. Non-zero determinant and elements in F. Okay. So now let's get to some problems. Okay. So there's actually not too many. Oh, why did I say that? There's not too many problems. Well, yeah, because on the first page there's only 9. But there's actually 32 in the whole section, so we're going to be here for a while. These first, 4 are really easy. Let me take a sip of water. So now, we're defining our operations as follows. So 3.1. And we're looking for which ones are associative. We're looking for commutative and identity. Okay, I'm going to label this as 1, 2, 3, and I'll have a check mark next to it. So for 3.1, m star n equals mn plus 1. So, is it associative? Well, let's check. M star, let's do A star B star C equals A star B C plus 1 equals A B C plus A plus 1. Now let's check A star B star C equals AB plus 1 star C equals ABC plus C plus 1. So, 1 is not associative. Let's try M. Okay, so now let's look for commutativity. A star B equals AB plus 1. B star A equals BA plus 1. Since Z is a field, it is commutative, so AB equals BA, so AB plus 1 equals BA plus 1, so it is commutative. Okay. Alright, now let's check identity. So what would our identity? We have an initial guess. It could be 1. Could be 0. Let's try 0. No. Pretty sure there isn't an identity, but I mean, let's look. N minus 1? No, it has to be a unique element. How would I prove that there isn't an identity? Oh, it's not asking for a proof, but I'm just going to say there's no identity. If I would prove, I would assume a contradiction, basically. Assume that there is an identity, show that it leads to a contradiction. And yeah, but in this case there isn't. At least not that I can think of. Alright. Next question. So M star N equals N plus M over 2. See, what are the... Why are there so many problems? Jeez. I mean, some of these are really easy though, so you should be able to get through most of them. I know I'm not talking loud. It's because I don't have the energy to talk loud for, I'm going to plan on doing 15 hours today, tomorrow 15 hours, 15 hours maybe on Tuesday, or not Tuesday, whatever. Yeah. Okay. So, what happened? Oh, no, yeah, there it is. Okay. So, associative. Let's do A star B star C equals A star B plus C all over 2, which equals A times A plus B plus C all over 2 equals 2A plus B plus C all over 4. Okay, now let's try A star B star C equals A plus B all over 2. I can already tell. Plus C all over 2, which equals A plus B plus 2C all over 4. So it's not associative. Commutative, I think so. A star B equals A plus B over 2, B star A equals B plus A over 2 equals A plus B over 2, because field properties of integers. In identity, okay, so this one I think there is one. I think it's 0. No, it's not. It's not 0. Would it be negative? No, that's the inverse. Yeah. Okay, there is none. No identity. It's not asking me to prove it, so that's why I'm not going through the whole proof. But if I were, I already know how to prove it. Alright, 3.4. No, 3.3. So n star m equals m. That's interesting. So let's check associativity. A star. I don't think it's associative. RC equals A star B equals A. A star B. So I don't think it will be commutative, or it's definitely not commutative, but it is associative because ordering really does matter. So this is going to be A star B equals A. So it is associative, but it's definitely not commutative. Just you can tell. Then identity. Anything's the identity. So since anything is the identity, it definitely wouldn't be a group, but it does have an identity, which is, you could just say anything. Oh, no. There is no identity. Why? Because m star e would have to equal e star m. Has to be commutative with identity. But it's not, so there's no identity. Alright. We're done with that. .4. Equals equals A star BC squared equals AB squared C to the 4th. Probably not associative, but still gotta show it. Yeah, not associative, but I think there is an identity. Well, yeah, there is an identity. Is it commutative? Let's check. I think it is. A star B equals AB squared. B star A. No, it's not commutative. B A squared. Not commutative. Not associative. Not commutative. But there is an identity. Right? Well, let's check. Let's say it's 1. Star 1 equals m. 1 star m equals m squared. Okay. So there's no identity. So it's nothing. It's a useless operation. Completely useless. Boring operation. Hopefully you'll hear some amateur saxophone playing. That's my brother learning saxophone. He got for Christmas. A squared plus b squared. Oh wait, what am I doing? Yeah, it's different. That's not associative. Commutative, though. Yeah, it is commutative. Identity. I think it's 0. No, there's no identity. Because m star 0 equals m squared. Oh, wait. N squared. 0 star m. Yeah, okay, there's no identity. Yeah, another useless operation. Man, so many operations are useless. Kind of ridiculous. Okay. M star n are 3.6. M star n equals 2 to the mn. Well, let's check associativity. A star b star c equals a star 2 to the bc equals 2 to the a, 2 to the bc. Okay, it's probably not associative. Equals 2 to the ab star c, which equals 2 to the 2 to the ab times c. Not associative. Kind of lame. Commutative, yes. Identity. Ooh, identity. No. Well, natural log of 2. Or natural log of 2. Would that be identity? No. No, there's no identity. So it's a useless commutative operation. I know, right? Imagine being a nerd. Okay, I think I just choked on something. Alright. So very few of these have had an identity. I think that very few of these have had an identity. Which is kind of lame, because identities are cool. So we're going to skip a couple, because we basically already done them. And we're going to go to 3.9. And the question is, does the ordered pair mn, mapping from m to the n, define an operation on the set of integers. So, so mn are in integers. So we have to prove basically that it's closed. So, which book am I using? Using Durbin because I had it lying around. And also Artin is just way too thick. This one has a lot of those feel-good problems. Basically, they're like easy to where I can do them when I'm brain dead. But it still has a decent number of proofs and stuff, challenge problems. Like it's not so easy that I won't learn anything. I'll definitely learn everything I need. But yeah, I just need to be able to get through some brain dead problems also because Artin and like all the other popular books have most of their problems are like not brain dead. I mean, you still have quite a few brain dead ones, but it's not like as many as are in here. Yeah, I think Artin's pretty alright. I like the spin on linear algebra that or not really spin, but they emphasize linear algebra. I'm already doing different linear algebra. So like all the algebra I need for linear algebra, I'm learning in a different book. So, because this book doesn't do too much linear algebra. Like it does like general linear group and a little bit of stuff with that. And towards the end, it does some stuff with like products and stuff, but overall, not much. Okay, define an operation. So is this closed? I don't need to prove anything, but it doesn't say prove, so I kind of wanted to say yes by obviously, but I guess I could maybe try doing a proof where I say assume that it doesn't. So like assume, oh wait, no, it doesn't. How did I say proof by obviously? It literally doesn't. If n is less than 0, then m to the n, not in integers, so doesn't define an operation. Okay. Proof, trivial. I'm not even kidding. This book does that so many times. That's the one annoying thing in this book is that in the answers, it's like trivial basically. So like, hold on. Look at this. Hold on. Which screen? I'll show it on the big screen. So this is in a later section. These are like the, oh my god. A later section. It says, these are the answers it gives, right? It doesn't give anything. These are just the answers. They say just... Oh my gosh. It's funny. That's funny. Like, even if they are trivial, they're just like little hints. I mean, I don't really mind. Alright. Well, let's go. Is there an identity for the operation in example 3.3? Yes. Yes, there is an identity. Wait. Oh, no. Yeah, it is. Identity for... Hold on. Let me check this again. What is the operation? Yes, there is. It's a IDS. Prove that there's no identity. Oh, we have to prove. I have to prove something. Oh no. Point 11. Prove that there does not exist an E in what is 3.2? Prove that there's no identity. The operation. Oh, for all positive integers, C plus, such that. 2 to the, or not 2 to the n to the e equals e to the n to prove that there does not exist. So, I mean, I could easily do this by just contradiction. Okay. Contradiction seems pretty easy. Yeah, just like let n equal 2. So 2 to the 1 does not equal 1 to the 2. Well, I guess I have to show that e would be okay, well, let's just see what properties n to the e equals e to the n would have. Assume there is an e equals n. Oh, yeah, okay. 2 to the 1 equals 2, right? And that's the only element that does that. So, or I guess I could say n to the 1. The only element, so I guess as a proof, this would be element in Z such that n to the e equals n is e equals 1, but if e equals 1, we have n to the e equals n equals e to the n equals 1. Contradiction. Thus, not true. They're yeah, just true. Contradiction proof. Okay. All right. So at 3 hours, I'm going to try to move to the next section, or 3 hours and 15 minutes. Has no identity element. We just did that. All right. Which of the following are true? So it's just a true or false, basically. Yeah, okay. All right. Complete the following statements. So that's if and only if that's not true for all. Blah, not commutative, if for all. And then if and only if, yeah, there's no identity such that. So these are just definitions. Like I said, these are the brain dead problems that I like because they're just definitions. Now, I'm sure later on it's going to be helpful to write out definitions. But since I'm already pretty comfortable with these, I'm not really skipping them. I'm just doing them in my head. All right. So this one's pretty fun. Complete the table. Make the table commutative. Now, I already know, sort of, that you need it to be symmetric along a diagonal, but let's assume I didn't know that, because I kind of I'm not sure about it. B, C, D, and we're already given A, B, C, C, D, A, B. It's like a Sudoku puzzle. That's what these tables are like. D. So we need that A star C equals C star A, which would be C. We need that B star A equals B star A equals A star B, which is B. D star A star D, which is D. Can y'all see this? Yeah. Then we need that B star C equals C star B, which is D. And we need this to be B. Okay. That's that was fun. So find the smallest subset A. So find A that's a subset of Z such that 2 is in A and 2 and A is closed with respect to what? Addition. Okay. Closed with respect to addition. So that 2 is in A and it's closed. So we can't get out of it. So one way to make sure we can't get out of it is just make sure that we don't include negative numbers. So yeah, just 0, 1, 2. Or I guess the smallest subset would be no, it wouldn't be that. So if I had 0 and 1, okay, 2. This is not closed. Is it? No, if we add any, if we added this to itself, we get 4. Okay, and we get 2 for this. So we get 4, so we need 4. But now if we add this, okay, so equals 0, comma 2 to the I, where I goes from 0 to infinity. That doesn't seem right, but because we wanted the smallest subset, you'd think you could come up with something finite. So maybe I can come up with something finite. That went for really big really fast. But we need something containing 2. So I mean, obviously if we just get rid of 0, we just say the powers of 2. That's our first guess. It's just the powers of 2. A equals 2 to the n, where n goes from 1 to infinity. So that's our first guess. It's just the powers of 2. But obviously that's not a good guess because it's not even finite. So we need to find let's try to find just a finite subset. So we need A equals 2. And then we need 4, because if we add it to itself, 6. Add it to itself, we get 12. Add this to itself. So the cardinalities of these sets are the same, though. That's the thing. If we say even numbers and powers of 2, their cardinalities are the same. So it really doesn't matter if we used either of them. I guess this one's less dense, but smallest subset. So I need to find something finite. Yeah. Oh, wait. 2 plus 2 plus 2 is 6. Oh, okay. Yeah, I guess. Because this is a subset of this set. So I guess you could say this one would be the quote unquote smallest. Powers of 2. I just feel like I should be able to find something finite though. Just wait on. What am I doing? Hold up. Why would it be powers of 2? Are you kidding me? I'm small brain. I'm small brain. Oh my goodness. It is even numbers. Hold on. Let's go back to the drawing board. Let's have 0 and 2. We need 4, since 2 plus 2 is 4. 4 plus 4, 2 plus 2, 2 plus 4. So we need 6. We need 8. So we need all the even numbers. And yeah, we need it because you always need to be adding 2. And these are all these multiples of 2, so they'll be included later on. So yeah, just even numbers. So I just want to say just the even numbers are the subset. It's weird. I feel like I should be able to find something finite. Okay. Alright, determine the smallest subset B of Q. So now we have rational numbers such that 2 is in B. And we have addition. So 2 is in B, but we have Q. So this is 3.20. So, and it's closed with respect to division, addition and division. Addition and division. So if we divide two things, we don't get outside the set. Okay. So let's have B just equal to set 2. Now it's not closed, but why is it not closed? Well, if we did 2 divided by 2, we'd get 1. And if we did 2 plus 2, we'd get 4. But also if you did 2 plus 1, you'd get 3. But also if you did 2 divided by 3, oh my goodness, this is ridiculous. I just want to say the positive rational numbers, because like you can get every single positive rational number. You just add 1 and 1, right? And then you just divide. You do the diagonal argument essentially. 2 over 1, 3 over 1, and then 1 over 2, 3 over 2 over 2. So positive rationals. Q plus. Right? Q plus, I mean, obviously it's not the smallest subset, I feel like, but it is a subset such that it's closed with respect to addition and division. Because we can't get negative numbers and we can't get any irrational numbers. So, I kind of want to leave it at that. Okay. Alright, how many different operations are there on a 1 element set, a 2 element set, and an n element set? So how many, what does that even mean? How many different operations let's see remarks in this example. 3.4. Is there a remark? Does it say that? Hold on. What does it say? How many different operations? Oh, they're ordered pairs. Okay. An element set. So, in a one element set, there's none, because you need two things for a binary operation at least. Oh, I guess, yeah, I would need to prove. I mean, it doesn't ask me to prove it, but at the same time it says determine, so I guess that is proving it. So let's just say Q plus, is it the smallest element? Assume that there is a set smaller. Assume that there is a subset. I don't know. Q. That's not a good name for it. R. No. I don't know what to call it. A. Assume A is a subset of Q. And A is closed with respect to addition and division. Okay. Yeah. So I would want to show, well, I'm trying to show by contradiction that if there is something smaller that it equals Q. So that's one way. So I'm assuming that it is strictly smaller. I guess the contradiction would be assume that cardinality of A is less than cardinality of Q. No, that doesn't even make sense because it's probably infinite. That doesn't make sense. Okay, don't worry about what I said there. But yeah, just assume that it's a subset. So what would that mean? Well, that means there are no negative numbers, no divide. There are all the fractions. So I'll pick an element, an A. I'm gonna try to prove that Q is actually a subset of A. Okay, yeah, I see what you get there. Okay, give me a second to just chill and then get back to work. So assume let just I don't know, A be an A, or let's do two elements, A B be an A. So we know that A plus B will be in A, and A over B is in A. Okay. I guess I could put so this. So A plus B is an A. Then we got, now we would say that we also know so we show that everything in A is actually in Q. So So wait, hold on. I just show that everything gets mapped to Q. I'm falling asleep. That's not good. Hold on, let's see the time. Oh boy, we gotta get moving. Hold on. There's so many problems in this set. Hold on, let me see how long the next set is. Okay, it's a lot shorter. Okay, so I can spend a bit more time on this set. I might do another 30 minutes. Okay, so we know that a plus b is an a, and a over b is an a. Okay, I mean I could let c equal a over b. So how would I show? Hold on, I need to stop looking at this and just try to show that Q is a subset of A. Okay. So we picked something in A. That's where I messed up. Why would I choose A? Of course. Let's just choose Q. And then show that it's in A. So show that is in Q. Show that it's in Q. Okay. Now how do we get to A? We know that it's closed. Or Q plus. Yeah, Q plus. Try to show Q is a subset of A. Okay, so we're trying to show that Q plus is a subset of A. And so we know that A plus B is in Q plus. So how do we get from there to Q to A? That's what I'm trying to wonder. Well, we know that Q is closed, so we can't get. Oh, okay, we can't get outside of it, but I'd still need to show it's a subset. So we have to show. Oh, okay, yeah, we just have to show. What am I thinking? We just have to show that this is in A, and what? I had a train of thought and then I completely forgot it. Oh man, okay, no, we have A plus B is in Q. A over B is in Q. I need to stop looking at this and look at this. Q is a subset of A. So we need to show that everything in Q is inside of A. How do we show that? Well, we know it's closed, so we know this. So now that everything in Q can be written in this form, right? Everything in Q is written in this form. Hey, I'm not giving up. Well, I might give up on this question because I want to move on, but it's because I'm looking at this wrong. I need to rewrite this question. So we're trying to prove that let like A be a subset of Q. Prove that, or Q plus really. Prove that Q plus is a subset of A. And we also know that Q plus and A are closed. So maybe that's the key. We know that if we take two elements, A, B, and A, we add them, or divide them, we get another element in A. Okay, which is also, but it's also in Q. Q plus. Because A is a subset of Q. How does this help? I don't know. Okay, that's a good place to start. 2. 2 is a subset of A. And then, well, we divide. We can divide by 2 and we can add 2. So we get 1 and we get 4. We can divide and we can add everything. We can just add 1 over and over. We can also divide. We get 1 over. We can do the diagonal argument basically. So 2. And we get so even though we count things multiple times, and so we know that this is a subset of A, but this is just Q. This is just Q, so Q is a subset of A. Okay. That was simple. Okay. This whole thing is just Q, but this is a subset of A, so Q is a subset of A. It's as simple as that. Okay. I don't know why I spent so long. You know my brain is already fried whenever I miss something like that. Okay. Alright, moving on. How many different operations are there on a 1-element set? None. You need 2 elements. A 2-element set, 1. A 3-element set. Oh, okay. So we have 0, 1. That's our sequence so far. And then on a 3-element set. So let's try this. X, Y, Z. We can have X, I don't know, star Y, X, star Z, X star not X. Well, yeah, X star X. Right? Yeah. Oh. Oh, okay, yeah, you need 1 in here. On a 2-element set, it would be 2. Wait, no, it's 1, because they have to be different. Oh, no, it's an ordered pair in the Cartesian product. So in a 1-element set, you do the Cartesian product. So you have, I don't know what I'm thinking, yeah. Oh, I'm sorry, yeah, I should have said Q plus, don't worry. Okay, so like this is our 1-element set. So where an operation star goes from Cartesian product x to x. So that's only one thing, one possible operation. I'm going to call it star 1. So there's only one operation, so 1. Then if you have 2 things, x, y, we have star 1 maps from x to, well, I'm going to call it s. Or I guess it could be xx, which is in s cross x to
S, S1, S2, XX. It could be star 2 is XY, star 3, YX, star 4, Y, Y. So we have 1, then we have 4. Now what about 3? So I think it's going to be something like n to the n for an Sn, or yeah, so star. Yeah, because it goes X, 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 Y. Yeah, it's going to be 3, 4, 1, 4, what is it? Go up to, or this would be 27, n to the n. Okay. Do I need to prove that? It doesn't say, so I'm just going to assume it's that. Close? Did I miss something? Maybe I did miss something. Maybe I have to divide by something because of order. It's not quite right? Okay, we're not done yet. So we have, let's go back to the 3 case. We have star 3. So S3, we're going to call it an element X, Y, Z. We're going to define a star 1 to be, oh. Oh, okay. We have to take a Cartesian product. So it'll be X, so it'd be X, Y to some S, X, Z to some S. Because we're not taking 3 things. So we do, or XX to S. Or this star 2, star 3, star 4. This would be like Y, X, 5. This would be like Y, Y, and Y, Z, Z, X, Z, Y, Z, Z. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9. So we have 1, 4, 9. Ah, okay. So I want to guess that it's n squared. That's my guess. And that would make a lot more sense because it's 2 operations. You're picking 2 things. I got the n to the n because I thought you were choosing like n many things, but you're only choosing 2 things, so that's why it'd be n squared. So that's how many operations. It's the number of arguments. Then wouldn't that be the number of operations too? Oh, I guess they have to be closed. Well, I should be grateful because I have someone checking my work. So I should be grateful, not upset. Because if I was doing this on my own and I kept getting things wrong and not knowing it, then that'd be bad. So that's 2 different operations. Okay. So hold on. I know I'm looking at the chat really funnily. So we've got two different operations for star 1 and 1. It could be 1 or 2. Hold on. Okay, let me simple this down. Star S2, right, equals x and y. So star 1 is going to map from XX to S. It can be either X or Y. So, and then star 2 can map from XY. So you pick X and Y, and it maps to S. It can be either X or Y. YX goes to S, so it can be either X or Y. And then Y. So the number of arguments is n squared. That's the number of arguments. So how many operations? You've got, in a set of 2 elements, that's 2 operations. 2 different operations? Oh, wait, what did I say? I said 4. Because some of them are the same? Yeah. They I feel like that's something like that because some of them are the same. So, but how would I just gave 2 examples. You said star 1 1 can be 1 or 2. There's way more. Huh. Well. Oh, that's funny. My headphones disconnected. Okay. So yeah, there's 16 total, but there's 2 distinct operations. So which one? It says, oh, how many different operations? Well, I'm not completely sure of what you're trying to get at. Well, I think I am, but at the same time, I want to make sure I get this right and not confuse it with something else. So in a set of 2 elements, we have 16 different like ways of pairing things, because we can go from XX to either X or Y, or yeah, I know why we have 16, because we have 4 different arguments that can be 2 different things, so it'd be 4 squared. Okay, so we have, but how many distinct operations? Oh, they're different. Oh, okay. So it is. So 4 squared. So we have the number of arguments. So it's actually n to the 4. 16. Because we have n squared different arguments, and then. Oh no! It's not n to the 4. We have n squared different arguments. Okay, n squared arguments, and then we have how many outputs, which is the number of elements in the set, which is n. So n to the 2n. N to the 2n, right? No, wouldn't be n to the 2n. It'd be n to the... Hold up. We have... Yeah, it would be n to the 2n, because... Yeah, n to the 2 times n. N squared arguments, and then each one can spit out n different things. But I flipped the thing? What did I flip? We have n squared arguments, and then we have n outputs. So it would be n to the 2n, or to be n to the n squared. N to the n squared? Oh.
Oh, it's n to the n squared. Okay. I think I get that now. Yes. So we have 1, 16, dot, 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 n to the n squared. And now I get that Cayley table cubed. We have n squared inputs and n outputs. Okay. Okay. It should be n to the n squared because the Cayley table thing also matrix stuff, the stuff you said about Cayley tables, that would also be the same thing, right? You have an n by n, so you have n squared, and then you have n different ways to arrange it, so you have n to the n squared. Okay. That's it for that question. Oh boy. So now we do the same thing, but for commutative operations. Oh boy. We spent 15 minutes arguing, or not really arguing, just making sure. You know what? I shouldn't complain. I'm not complaining because I would rather get things right and learn it properly than to just speed through it and actually not actually learn it. Okay. So how many different commutative operations are in an n element set? So now we change it to where the things are commutative. So let's start with the S1. Let's start with the S3 case, or I guess S1. Right? We've got one element, so it can either x, and it can just be x. Okay. And that's commutative. Because if we only have two ways to be x and x. I guess I could use the Cayley table. So it says use the Cayley table to help out with this one. Might help. So for a Cayley table, right, we have x1, x2. We have our operation that maps from Cartesian product and we're dealing with a finite set, I'm pretty sure. So that symmetry has to be, I'm going to assume that this is the identity element, but I'm pretty sure it has to be something like, this has to be x1, x2, xn, x1, or it's basically when each different one is an identity. Wait, no, we don't need an identity. That's for a commutative group, for them to have a thing like this, where this is a x2. Wait, no, this would be x1. x1. That's not right. Not sure what I'm doing here. Wait, what am I doing? What on earth? No, this is wrong. x3, x4, x. Okay, this Cayley table has not helped at all, so let's try something else. Let's go back to the S1 example, or let's try an S3 example. S3 equals an element set with three elements, x, y, z. Okay, so we have x, y, z, and what's the question? So it's the same as before, but now we only have a commutative operation. And we're trying to see how many different commutative operations there are possible. So I'm going to go ahead and I'm just going to do a Cayley table for 3 by 3 because I think I was trying to generalize it too soon. So let's just play the Sudoku puzzle multiple times. So you have x, y, z, y, z, x, z, and then z. Oh wait, no, this can't be x or z. This would have to be z, x, x, y. Okay. So what do I notice about this? Well, let's try it with a different identity. Or not really different identity, but we know since operation has to be closed. So let's try it. Let's just say this is y, this is x, z, this is x, this is y, this is oh no, this would have to be z. So z, this is y, and this is x. So I could do the same thing. I think I'm getting there. This is just a long way of doing it. And it doesn't ask me to formally prove it, so I think this is a fair strategy. So now we have z, y, x, y, z, z. We could swap these diagonals. They could be y's. So I'm going to say 6 or n factorial. Nah, I don't think it's n factorial. But I do want to say 6 because if you have this one, right, let's just say x's identity. Let's switch to z's and y's. It's still commutative, right? Z, 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 y, y, y. Right? So we switched the z's and y's, and it's still commutative. So we see that it has to be the diagonal has to all be the same. Has to be like this. So it's of the form. We have xn. We have some element xi, way up here. Then we have along the diagonal, we have x1, x2, or any x, xi1, xi2. Okay, so it's getting kind of complicated when I try to generalize it. But let's just go back to this example. We can swap the x and z's if we put x's identity. We can swap the y's and x's. We can swap. So basically, we set one as identity. There has to be identity because we're assuming it's commutative, right? And so a star b will equal b star a, right? And it'll equal some element e, which is identity. It might be something else. So it has to have an identity. No need for identity? Okay, never mind. Hold on, let's just see. But we can tell that it has to have this kind of thing, right? Where you have same elements like this. Has to look like that. And how do I know how many numbers or how many different ways you can arrange these things are? It's the number of ways you can arrange 3 lines. So it's just n factorial. Right? I mean, that seems too big though, but it makes sense. Like, my argument makes sense to me. Because you have these 3 lines and you're basically just permuting them. But I feel like these 2 lines, the way you arrange these 2 things is what changes them. Hold on, if you change this line to this line, then you basically put it over here. You change this line to this line, you basically put it right here. It's like scooting them over. It's a different operation. You change this line. Hold on, no, it might not be n factorial, but n choose 3? Or n choose n? No, it's not n choose n. Or number of combinations. No, it's definitely not that. It's too small? N factorial is too small? Wow. Okay. We have 3 different things. If we move it here, well, also we can change it. So I think it'll be 2 times n factorial. That's just a random guess. Yeah. And n factorial is really big. Like, that's my initial guess, is n factorial. Oh boy, I've got to get moving on to the next section. Nope, I need to stick with this. Okay. N minus n factorial. Oh wait, hold on. N to the n. Okay, yeah. So it's not as big. Oh, okay. So, let's go back to this permuting example, right? So we have n factorial permutations. Or not really permutations, but just way to arrange these 3 lines, right? That's the symmetry we have. I feel like if we can also multiply it by 2. No, hold on. Move this line here. Move this line here. Move this line here. Well, I mean, that's what I'm thinking. We have our Cayley table over here. You can't see it. And I'm saying that, so for how many ways are there to fill a top half of a Cayley table? You have like 3 lines. You gotta change them all around. So that's n factorial, right? Upper triangular part of a Cayley table, yes. This part right here, above this diagonal, you have
you have n many. Oh, wait. Okay, hold on. No. How many? In this case, you have 3, but let's try the 4x4. You have 1, 2, 3, 4. Okay, yeah. You have n many diagonals. So the upper part, you have n many diagonals, and so you have to permute them n many ways. The whole matrix is n squared. Oh, so it's n squared over 2. N squared over 2? How much above the diagonal? Yeah, n squared over 2. So then that factorial. What? That doesn't make as much sense as what I had. What if n is odd? I'm hungry. That's what n is. Come on, brain, think. I'm not actually thinking, I'm just drinking. What if n is odd? How many parts are above it? So we have n squared over 2. Okay, that won't work. N times n plus 1. N times n plus 1 over 2? Now that's always an integer, so that makes sense. So n times n plus 1 over 2, number of things. So then you factorial that. Each one has n options. Oh, yeah, so you're adding the numbers up to n. So it's... And then you factorial that, right? I want to factorial something. N times n plus 1 all over 2 factorial. Okay, that makes sense. Each one has n options. No factorials. Just remember the last problem. Right. There's no factorials. You just put it to the... that's the number of inputs. So you have n to the n squared. That doesn't... That's not right. You just square it. No. What am I doing? That's the number of outputs. So... number of total operations, you square it. Yes. No. I don't... what have I done? I've been handhelded through a whole problem that I thought I could do on my own, but yes. So you square it, right? No, that's too small. Hold on, you have n times n plus 1 over 2. Choose n? Outputs to the inputs. Oh, okay. Outputs to the inputs, so you have n squared. Oh. Wait, hold up. So we have more operations than we do outputs to the inputs. So we have n times n plus 1 over 2 to the n squared. Is that bigger than or less than n to the n squared? I feel like that should be it's bigger than, but we put an extra restriction on it. No, inputs. Oh. Okay, that makes more sense.
So then our outputs is, we have n different outputs. I'm busy. Inputs is n times n plus 1 all over 2. What was our outputs, which was n, right? Yeah, just n, or n squared. So it's n to the n times n plus 1? Okay. Okay, I finally got it. Over 2. No. Yes. Something like that. We did it. We did it. Barely. See, like I said, there's a decent number of problems that will make you think a little bit. But for the most part, like this next problem, it is brain dead simple. So prove that addition in M to R is commutative. Yeah. So we gotta prove that M2R is commutative. So I mean, I guess I can represent that with matrix AI. Or no, I don't even need AI, but let A equal this. A11, A12, A12. A21, A22. I think I messed that up. You know what? Screw this. Just do the old algebra way. A, B, C, D, and then B equals C or E, F, G, H. Okay. Add them. A plus B equals A plus E, B plus F, C plus D, D plus H, then B plus A equals A plus, or equals E plus A, F plus B, D plus C, not D, G plus C, H plus D. And since reals are a field, is a field, A plus B equals B plus A. I know that's kind of cheating, but we haven't gotten to fields and stuff yet. So, yeah. Did someone just unlike my video? Reported. Okay, we're at 38 minutes. I'm going to do 2 more problems from this section. So we have that assume
that what is it? Star is an operation in S with identity E such that what book do I use? I should have put that in the description. Thank you for reminding me. Putting that in the description right now. So that way let me quickly edit that. The book I am using is Modern Algebra by John R. Durbin. What edition was this? 5th edition, I believe? Yeah, 5th edition. 5th edition. There we go. I can't believe I forgot that. Okay, let's move that over here. So yeah, it's the Durbin Modern Algebra 5th edition. Okay. E such that X star, my marker is giving out. After this next section, I'm going to go grab some water and markers. Z, unless I have some here. Wait, I do. I have a marker. Okay, I don't need to grab anything. Equals X star Z star Y. So we've got that. So now we have to prove that star is commutative and associative. So part 1, commutative. Oh, much better. Part 1, commutative. So to prove that it's commutative, we have to show that let A and B be in S. We have to show that A star B equals B star A. Well, this is easy because we have an identity element. So what we can do is we know A star B star E equals A star E star B. Oh, that doesn't help. Well, how would that help? No. Let Y be the identity. Yeah. No, hold on. So I have to prove associativity and commutativity. Well, that's how I'd prove associativity, but how do I prove commutativity? Nice. Multivariable calculus. It's not easy. I mean, I got an A in the class, but it was a hard-fought A. It was not an easy A. Whereas linear algebra was kind of an easy A, but
multivariable calculus is definitely not easy. So it's very tedious. I mean, the concepts are yeah, I guess it also conceptually kind of hard because everything's in 3D. Whereas with linear algebra, everything's just so abstract you can't even think about it. You just have to work with the abstraction. So I guess linear algebra is harder for other people because they're not used to the abstraction. But for me, since I was used to it, it was a breeze. Yeah, ultra tedious stuff. Okay, so which one should I pick for identity? Oh, pick X. Okay. We know. Okay, so okay. Let X equal E. We know E star Y star Z equals E star Z star Y. So Y star Z equals Z star Y, since Z, Y are arbitrary. S with star is commutative. Okay. Now, associative. So now we're going to have to show, so I think we have to show that parentheses don't matter. So, I mean, I could introduce a W. Or how about this? I say let Y equal E. I mean, I guess that makes sense. Oh, yeah. Let Y equal E. I mean, this will just mean X star Y or E star Z equals X star Z star Y or star E. I mean, it just means that X star Z equals X star Z. But I think, okay, hold on. Let me just work with what we need to get. We need to show that A star B star C equals A star B star C. So we're pretty close to that already. So what we can do is well, oh wow, it's almost 4 hours in. Oh wait, we're on our last two problems. And the next section isn't too long. So what is it? So we have this identity. We know we know it's commutative, so we can just move things around. Okay, duh. No x star y star z equals x star z star y. So no, it's commutative. So we could do almost there basically. Oh, we know it's commutative, so we could just do we have to show that this would be z star y. Well, no, we can switch this around. So x star z star y equals x star z star y equals x star z star y. There we go. Okay, that was, yeah. I didn't even have to look at chat, but yes, that was the secret. Really obvious. Okay, last question. Assume E is an identity. Okay, so we're basically proving that left inverses and right inverses have to be equal sometimes, or most of the time. So assume E is identity of S. Prove that if star is associative, B star or B is left inverse. B star A equals E. Basically B is left inverse. C is right inverse. A star B equals E. Then, or A star C. C is the right inverse. Then B equals C. Okay, so prove that. That's pretty simple. Because we have associativity. So we can substitute that. We know that this is E, so we know that B star A equals E, or which equals A star C. Okay, no, that does not. Well, it might help, but that's not going to prove it. We need to prove again. We need to prove that B equals C. So we just show that since B star A equals A star C. So we know that. Now we just need to prove that B equals C. And A, B, C are in S. So I guess I could star E on both sides. And since it's associative, oh, yeah, that's the trick. I don't even have to star E on both sides, but it basically helps. We have B star A, B star A star E equals A star
C star E. Yeah. We could basically start anything, but like, hold up. I almost have this. I know I do. Okay, we almost have this. Come on. B star A star E is. Oh, we're almost at the 4-hour mark. I can get this before the 4-hour mark. I know that for sure. B star A star C. Okay, we're trying to get rid of this A. How do we get rid of this A? Well, I guess we could just start with B equals C star E. Like, we're assuming that's true. No, we can't assume that's true. But, like, if we work backwards, what do we get? Well, hold up. B star A is E and A star C is E. So since it's associative, we have C star A or B star A. We have C star E equals C. Okay, how does that help us? Well, that means that equals C star B, because it's associative, star A. So C star B is also the left inverse of A. Okay. How does that help us? Well, we know that C star B star A equals C star A star C. Okay. Because of associativity, we have C star B star A equals C star B or star A star C. That does not help. Well, let me think through this again. What do we want? We need to show that B equals C. Well, I guess we could assume that they don't. Assume B does not equal C. Okay. How does that help us? Well, we know that B star A star equals E star C. Well, I guess equals E star C. Okay. Oh wait, no, it doesn't equal E star E. What am I thinking? Equals C star A, or A star C. We're almost at 4 minutes. Or 4 hours. A star C. Come on, I want to prove this. I will get a sweet release of dopamine if I prove this. We have B star A is C. No. A star C. I mean, if we start with A, we know they're different though. To show that this leads to a contradiction. So if we start, so B star A, it's not equal C star A. Okay. So we have E is not equal C star A star E. That doesn't help. None of this helps. Okay, we're at 4 minutes. The question I got stuck on was prove that left inverses and right inverses are equal when there's an identity and associativity in a set. Okay, so I'm moving on to section 4. Oh, wait, hold on, I need to here. Boom. Okay, I'm also gonna pause for a second. Let's just say flip the thing. Yeah, I flipped the thing. Alright, I'm gonna be right back, and I'm gonna like turn on some AC, turn on some lights, and use the restroom. So I'll be right back. Mom, I already oh.
So after the first chapter, I'm going to do what's called a piano break. So like after the next section. So stay tuned for that. What does a piano break sound like? Well, sounds like me playing piano. That's what it is. You know, me doing... Okay, I'm done with the quick piano break. And now we are moving on. Okay, and I split. Alright, composition. So, put away the whiteboard, take out some notes, and this part. And we're just going to do some notes. I need light actually. Let me turn on some light and a fan. Okay. I hope the fan noise isn't too annoying. Alright, let's get going with this. M of S. Mappings from S to S. Okay. Theorem 1. Theorem composition. Composition. Oh my goodness. Okay. Composition is an associative composition is an associative operation on, okay, so it has this capital M of S. Let me see what that meant again, because it was brought up in the last section. M of S denotes the all mappings, the set of all mappings. M of S, so all mappings beta of alpha from S to S, so that beta of alpha is in M of S. Okay. It's associative on MS with identity IDS. IDS. Okay. Composition is an associative operation on the set of all invertible mappings. So B associative invertible mappings. Notice how the timer still runs. Oh, you gotta go. Notice how the timer still runs as I'm learning and taking notes, because that's the whole point. It's not just doing problems, it's also the learning part. So even while I'm writing down my notes. Okay. Identity IDS. Okay, proof. Alright, so let's prove this theorem. So basically, we write gamma of beta of alpha of x equals gamma of beta of alpha of x equals gamma of beta times alpha of x equals gamma of beta of alpha of x. So part 2, the proof. Oh, M of S is capital M of S is like this set that describes all mappings from S to S. That's a good definition. Okay, so we have an example. Let P denote a fixed point in a plane, and let G denote the set of all rotations of the plane about the point P. Each element G represents an element M of P. Agree that two rotations are equal if they differ by a multiple of 360 degrees. Then composition is an operation in G. If alpha and beta are rotations about P, then beta composed with alpha is a rotation obtained by first applying alpha and then applying beta. So you just add the angles. Okay. For each another example. So for each ordered pair AB with A not being equal to 0, let alpha AB go from R to R, defined by alpha of AB of x equals AX plus B. Someone just sent me a message that I probably need to read. So, oh my goodness, I have like okay. Alright, notifications are all, oh my goodness, who's texting me? Okay. Alright. So let H denote set of all such mappings.
composition is an operation. To verify this, let A, B, C, D be ordered pairs of real numbers with A and C. Then AC doesn't equal 0. So alpha of AB composed with alpha C, D, X equals alpha A, B of alpha C, D of X equals alpha of A B of CX plus D equals A times CX plus D equals ACX plus AD plus B, which equals alpha AC AD plus B of X. Okay, alright. So the first problem dude, this guy loves Greek letters. Whoever was the author of this, you love Greek letters, don't you? Okay. Oh wait, I just realized that's a problem. Alright, let's get on to problems. So I already finished reading this section. Magnification, translation. Okay. I kind of see what it's getting at there. Alright. Let's do okay, we got that. Now let's get on to some problems. Okay. With S, we have S equals the set AB the set MS, or the set of all compositions, contains 4 elements denoted by this pi, rho, sigma, tau. Like I said, this guy really loves his Greek letters. So we have pi of A equals A, rho of A equals A, sigma of A equals B, we have tau of A equals B, pi of B equals A, rho of B equals B, sigma of B equals A, and tau of B equals B. Okay, yeah, like I said, this guy really loves his Greek letters. Okay, so A, construct a Cayley table for composition. Okay. So composition. We have to find compositions of everything. We have composition. We have pi, rho, sigma, tau, pi, rho, sigma, tau. Alright, so pi of, okay, so we basically have to go through all the combinations. So this will take a little bit, but I can do this. So pi of A is pi, wait, hold on, we know that pi, start with pi composed, oh wait, no, pi of A equals pi of A, yeah, because pi of A is A, so it's pi of A, which is A, or pi of A equals pi. Pi of rho, so rho of A is A, so pi of rho is pi.
pi of sigma. Oh wait, no, that's not right. Should be rho. Sigma of A pi. No, it'd be sigma after. Okay, this is confusing. Hold on. Pi of sigma of A equals pi of B, which equals A. So pi of B, which is A, that doesn't make sense. How about we do sigma? Sigma after pi of A, which is sigma of A. So that's sigma. This is tau. It seems to make sense. Pi, rho, sigma, tau. But at the same time, I did list the books I'm using. It's in the description, or at least it should be. If it's not, then go ahead and tell me, but it's at the bottom of the description. I should have put it at the top, but I completely forgot, so I put it at the bottom. Okay, hold on. I need to prove this part first. So rho after pi of, okay, it's saying that rho after tau, rho and tau, rho after tau is tau. Okay. So let's work with that. And it says that rho after then sigma after tau is pi. Okay. I have no clue. I really don't know. It is probably downstairs in the wash. My best guess. Okay. Okay, hold on. So rho tau. So tau of tau is either pi. This tau. On rho of tau of A equals rho of B, which equals tau. So rho of B equals tau. And then rho of B equals tau, so pi of A is A. Hold on, sigma after tau. The sigma of tau of A is it's a sigma of tau, which is tau of A, which is B, which equals pi. So I'm getting stuck on this first problem. It's already been 20 minutes. Now I want to say something like this. This would be oh well, my rows are okay. So not commutative. Which ones are? Yes, it is commutative on invertible. Okay. So next one is just the same problem, just with more stuff. All right. Let's get to a proof. Bro, I could fall asleep right now. That sounds so nice. Just stay awake. I need some inspiration. Okay, hold on. So let row 90 be the clockwise rotations. Okay, so construct a Cayley table for clockwise rotation. So we have row 0, row 90, row 180, and then row 270. Row 0, row 90. So row stands for rotation. Row 180 and row 270. So this is obviously going to be our row 0. This will be row 90 because row 0 is the identity. Row 180. This will be, oh man, I just realized I'm not showing it because I went sideways. I was upside down. And then this will be row 270. This will be row 90, row 180, and row 270. This will be row 180, row 270, row 0, row 0, row 0, row 270, row 180, or no, row 90, row 90, row 180. Commutative, yes. Identity element. Does each element have an inverse? Yep. Inverse of 180 is itself. Inverse of 270 is 90. Inverse, yeah. Okay, so it's a group. Okay, I have to actually do this question. Let S denote a non-empty set. Let S be non-empty. And let capital N of S denote the set of one-to-one, denote the set of injective mappings from S to S. Okay. Which theorems prove, so A, which theorems prove that composition is associative? So prove that composition is associative in a one-to-one set. Oh, my nose is itchy. So composition is associative operation on MS. So I guess theorem 4.1 with all invertible mappings. Well, it's associative operation. So yeah. Okay. On NS. Oh, one-to-one mappings. Oh, okay. Well, theorem 4.1b, because if it's one-to-one, oh, it's not necessarily invertible, but since it's S to S, then it is invertible, since it's all operations. So okay. Alright. Next question. I don't want to give up here, but we're so close to a nice break point. But I'm not giving up here. Okay. Let alpha denote clockwise rotations through pi over 2 radians. Let H denote the smallest subset of G, such that A is an H, and closed with respect to composition. Okay, and so on. Oh, consider example 4.1, which was the rotation one. Okay, so alpha is a set of clockwise rotations through pi over 2 radians. H is a subset of G, and then alpha is in H. H is closed. Determine H. So what on earth would H be? I'm gonna have to give it some thought, but not before I give it a rest. Doing math is tiring, you know? Who knew that doing math was really tiring? Okay, so alpha denotes clockwise rotation through pi over 2 radians. Such that h is closed with respect to addition. Determine h. So what would be like the, I guess, elements of h, or things such that you can't get outside of alpha? Well, no, we need all the rotations up through pi over 2, but also g, which is complete rotations, right? So h would have to be, if you compose pi over 2 with pi over 2, you get over here. So that has to be in the set. No, pi over 2, yeah. So you need the whole set, because if you have pi over k, also, yeah, that's the next part, is replace with pi over k. How many distinct elements? Oh, distinct elements. Oh, wait. Oh. Distinct elements means, like, rotation. No, alpha by alpha squared. Alpha. Well, alpha squared, in this case, equals pi alpha cubed equals 3 pi over 2 alpha to the 4th. That's just the same. So there are 3 elements, because you can't get anything else. So h is pi over 2 pi 3 pi over 2. Okay. And then with alpha as pi over k, we get 2 pi over k, 3 pi over k, all the way up through pi, all the way up through 2, wait, so we got to pi over k, 2k pi, or k pi over k, 2k pi over k. So we have 2k pi elements, or 2k elements. The order of h will be 2k, or not order, cardinality. Okay. Okay. Let A be developed following subsets of A. Okay, hold on. Actually, that's not too hard. What is it? Let B B and C be subsets of A, such that B equals the set A comma or alpha, and then A comma 0. A is in R, and A does not equal 0. That's B. And C equals the set alpha 1 comma B, such that B is in R. Okay, so A, verify that composition is an operation. So basically verify B is closed we take two elements in B, alpha 1, A0, alpha 2, A0, compose them, we get alpha 1, A0 of A plus 0 equals A squared plus 0 equals alpha of A squared. 0. Yeah. Okay. Alpha A squared 0. So that's in our set. So, yeah. B is closed. Then verify that, yep. Yeah, okay. Verify, alright, consider, let D denote the smallest subset of A such that A11, so D denote the smallest subset of A, a subset of A such that D, or what is it, alpha 1, 1 is in D, and D is closed. So determine D. Well, alpha 1, 1, what is that? That is 1 times x plus 1. Or x plus 1, really. So the set of all natural numbers is so n is in D. I think that is the smallest subset. Yeah, this is just the set of natural numbers. Okay. So and it doesn't say prove. If it says prove, like at the very beginning of the problem, then I will prove it. But unless it says something like verify or do whatever, compute, I'm not gonna do a full proof. Okay. Right into so let S be the set X is a member of the set of reals such that X does not equal 0 or 1. Okay. Consider the 6 mappings. We have alpha 1 of X equals X. Alpha 2 of X equals 1 over X. Alpha 3 of X equals 1 minus X. Alpha 4 of X equals 1 minus 1 over X. Alpha 5 of X equals 1 over 1 minus X. And alpha 6 of X equals X over X minus 1. Verify that okay, so we gotta construct. Oh, this is a long problem. This is a very long problem. But I will do it, because afterwards it's just some proofs, and then we'll be done with this section. at some linear algebra later on. So that'll be nice. Okay, so construct a Cayley table. So this will take some work, but alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Alright, so this is going to be a long question. I'm going to have a ton of side calculations and then just erase them. So let's just start from, and it's going to give us, it gives us a couple hints. Alpha 1, so this is composition. Alpha 1 composed with alpha 1 equals x of x, or equals alpha of x, which is just alpha 1. Okay, so this is obviously going to be identity. Alpha 1 to alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 1, alpha 2, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay, now let's check alpha 2 with alpha 2. I just realized I messed something up. So I should have slowed down. I should have slowed down. Okay. We have alpha 1. Okay. Alpha 1 composed with alpha 2 of x equals alpha 1 of 1 over x equals 1 over x. Okay, no, I shouldn't have slowed down. I was correct. I was correct. That is identity. Alpha 1, alpha 2, or alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay, so alpha 1 or alpha 2 composed with alpha 2 is also alpha 1. Ooh. Alpha 1. Right? Yeah. No, wait. Alpha 2 of x, or alpha 2 composed with alpha 2 of x equals alpha 2 of x equals x. Okay. So that's pretty cool. Alpha 3 with alpha 3. 3 of x is alpha 3 of 1 minus x equals 1 minus 1 minus x equals x. So this is also alpha 1. And I think this can just keep going. We have alpha 4 of alpha 4 is the same deal. It's going to be alpha 1, alpha 1, alpha 1. I think. I mean, I should verify. 1 minus 1 over 1 minus 1 over x equals 1 minus 1 over x minus 1. This will be x equals x minus 1 minus x all over x minus 1 equals x over x minus 1. Okay, so I was wrong. Hold on, let's I keep going things too quickly. So alpha 4 with alpha 4 is going to be 1 minus 1 over 1 minus 1 over x. okay, which equals 1 minus 1 or x 1 minus or x minus 1. So this equals x minus 1 minus x all over x minus 1 equals 1 over 1 minus x. So this is alpha 5. That's interesting. Okay. So now let's try alpha 5 with alpha 5. So 1 over 1 minus 1 over minus x equals 1 over 1 minus x minus 1, or this is x, or 1 minus x, which equals 1 minus x over negative x equals it's going to be alpha 4, right? Yeah. Alpha 4. Then alpha 6 with alpha 6 is going to be x over x minus 1 over x minus 1 minus 1 equals x over x minus 1 over x minus x plus 1 all over x minus 1, cancel these, equals x over 1 equals x. Okay, so that equals alpha 1. Okay, so next let's try alpha 3 with alpha 2. Which is hold on, I'm not convinced that alpha 5 with alpha 5 or alpha 4 with alpha 4 is, oh wait, hold on, alpha 4 with alpha 4 is alpha 5. Let me make sure I get this right. Alpha 5, alpha 4, okay. No, this is still good, yeah. So this can be alpha 4. So what is alpha 4 or alpha 3 with alpha 2? Oh wait, I already have that down. Alpha 3 is 1 minus x, or no, of x is going to be alpha 3 of alpha 2, which is 1 over x, equals 1 minus 1 over x, which is alpha 4. Perfect. And then so 1 minus x, so we have 1 over that, so 1 over 1 minus x, which is alpha 5. Interesting. Okay. So next we've got alpha 2 or alpha 4 of alpha 2 of x equals alpha 4 of 1 over x, which equals 1 minus x, which is alpha 3. Interesting. Okay. So this can't be 1 or can't be 5. That can't be 5, so this is alpha 5. It's like solving a Sudoku puzzle, basically. This is alpha 6. This can't be 1. Could be 2. Can't be 3, 4, 5. But it can be 6. This one can't be 6 though. And this one needs 6. So this one has to be 2. Or no, this one has to be 6. This one can be 2. Can also be, can't be 1. Can be 2, 3, 4. So it has to be 2. This one has to be 1, 2, 3, 4. It's like solving a Sudoku puzzle. That's what I'm doing, basically. I'm writing out a Cayley table for this set of symmetries, and it's basically like solving a Sudoku puzzle. Okay, so this one can't be alpha 1, so this one has to be alpha 1. So this one has to be alpha 1, 2, 3. This one can't be alpha 1. Could be 2. Could be 3. To work on it later. 1, 2, 3. I'm basically making it to where I don't have to do much more algebra. I just have to do the composition. Okay, because it's an operation. We verified that it was an operation already. Okay, so 1, 2, 3. Oh, we don't know about 3, but this one can't be 3. This one can be 3 though. So 1, 2, 3, 4, 5. 1. I guess I should do more work. Hold on. What about this one? Can be 1. Can be 2. I can. Okay. So let's do some work. So this one, alpha 6 with alpha. Which one's easier to work with? Alpha 2 and alpha 4. So alpha 2 of alpha 4, which is 1 minus 1 over x, is going to be 1 over 1 minus 1 over x. Didn't it already give this to us? No, it didn't. But it says alpha 6 with alpha 2. Alpha 6 with alpha 2 is alpha 5. I already got that. Okay. This equals x over x minus 1. So this is alpha 6. That really helps because that means that this one's alpha 4. No, can't be alpha 4. We need alpha 4 though. This one's alpha 4. This one's alpha 3. That makes sense. Alpha 4, alpha 3. So we have 1, 2, 3, 4, 5. 1. We need a 2. So we can't have a 3. So this one's alpha 3. 4, 5, 6. 1. Oh, this one's alpha 2. 1, 2, alpha 2. 3, 4, 5. Or 1, 2, 3, 4, 5. Alpha 6. Alpha 1. Then we have alpha 1 and alpha, or no, can't be alpha 1. We need 1, 2, 3, 4, 5. 1, 2. And boom. We just did it. I'm proud of that. My Sudoku, I mean, I'm not that good at Sudoku, but it helped. So, yeah, that's the Cayley table. Now it's asking, is it associative? Or is there an identity element? Yes, alpha 1. Show that each element has an inverse. Okay, inverse of alpha 1 is itself, because it's identity. inverse of alpha 2 is itself, inverse of alpha 3 is itself, but it gets different. Alpha 4, its inverse is alpha 5. Alpha 5, its inverse is alpha 4, and alpha 6, its inverse is alpha 6. Is it commutative? I want to say yes, because it's kind of symmetric, but at the same time, I kind of want to say no. Let's see, is alpha 4 this with alpha 3 the same as alpha 3 with alpha 4? Alpha 3 with alpha 4 is alpha 6. What's not symmetric about this diagonal? Almost is. Hold on, maybe it is. If these swapped and these swapped, then it would be. I think they can't. No, they can't. They can't. It's almost commutative, but it's not quite, so no. Alright, so that was a fun problem. So now let's move on to some proofs, and then we're done with the whole chapter. The first chapter out of a lot. We are barely getting started. But that just makes it more fun. Alright, prove that alpha, or if prove if alpha maps from S to T, beta maps from T to U, and gamma maps from U to V, or to V, or any mappings, then gamma of beta of A, or of alpha, equals gamma of beta of alpha. Okay. Okay. So this is more general of another theorem. So we can so first we have to show that these all map to the same thing. We're basically trying to show that mappings are just associative in general. So first, that they map to the same thing, to some beta of alpha of A, which is in T, so beta of T, which goes to U, so equals gamma of U, which is in V. So gamma composed with beta of alpha maps from S to V. So now let's check the other side. Gamma of beta of alpha is gamma of beta of some T, which is in T, which is gamma of beta of T, which is gamma of U, which is in V. So gamma of beta of alpha maps from S to V. So that was the first part of the proof. Second part, we actually have to show that it's equal for all things. So how do we show that it's equal and there are any mappings? Okay. It's already been 5 hours. Wow. Wow. Okay, so we're gonna do 2 more problems after this. Yeah. And then we'll take our piano break. Oh, okay, yeah. Oh, wait, what am I proving? Yeah. Yeah. So, prove that gamma. Okay, so. Can y'all see this? Yes, y'all can. Sort of. My handwriting's a bit iffy. Gamma. So, we're trying to prove that we pick an A that's equal for all A. Well, we know that there's an identity element, so I guess we could use that. IDV. So this is all in V, so if we do IDV, so gamma composed with beta of alpha of IDV equals gamma of beta composed with alpha composed with IDV. Or I guess, yeah, this. Yeah, that doesn't help. Well, what are we trying to show? We know that it's associative when the domains match up, when they're all the same. So we just have different domains. That doesn't really change anything. So let's go back to the example and the proof. So we can write basically gamma of beta of alpha of some x in S x in S equals gamma of beta of alpha of x, which equals gamma of beta of alpha of x. Okay. But that equals gamma of beta of alpha of x. But that just equals gamma of beta of alpha of x. So therefore it's associative. Boom. Okay, I didn't need to spend so much time on that proof, but yeah. It was just by definition. Okay. Alright, so this one's just a quick question. Is composition an operation on the set of all continuous mappings from R to R? Yes, because of intermediate value theorem or something like that. I don't know. Alright, prove. This is a proof that if a vector space that if a vector space V prove that if V is a vector space, prove that if V is a vector space, then composition is an operation on all linear transformations. Composition is an operation on the set of all linear transformations. Okay. All right. So yeah. What am I doing? I need to prove that it's an operation, so just prove that it's closed. So we have T, so mapping T of X, where X is in V, equals sum A times X, where A is a member of M N R N F. Okay. So AX, which is in, so T, matrix multiplication is literally defined to where T of S of X equals A times B times X equals AB X. That's literally how matrix multiplication is defined, so that this is true. So what is it? So it's an operation basically. Composition is defined, which is in V. So it is an operation. Now that wasn't an actual proof really, that was just more definitions. I guess it was a proof, but like wasn't. Yeah. So yeah, I guess that's it for that section. So composition, I'm feeling pretty comfortable with that. Obviously, composition is very important in category theory, but we're not doing category theory. We are just doing normal algebra. All right. So I'm gonna go. We are done with the first chapter, and I'm gonna quickly clean up a little bit. Let's go ahead and split. Boom. Oh wait, no, that didn't. Oh, it's not. Go here. Boom. 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 Okay. So I will be right back. Let me just pick up some stuff. I need that actually. Okay. Okay, I am back and I'm gonna do a quick piano break because I am extremely bored. Well, not bored, but it sounds weird because of the fan. Let's see. All right. Let's move on to the next chapter, which is Introduction to Group Theory. Now tomorrow I'm supposed to do like the rest of group theory, but today is just the introduction. Learn the basics of it, which is still pretty a decent amount, but all right. Introduction to groups. All right, and then let's go ahead and get this way. Grab some water. Okay. A group. All right, the definition of a group. A group is a set G with a operation, or with n operation star on G such that it it satisfies the axioms of associativity, existence of identity, existence of inverses, and finally, well, it has an operation, so it's closed. So, yeah, closed. So, examples. The set of even integers with respect to addition is a group, because the sum of two even integers is an even integer. The associative law is true for all integers, so it must be true to a subset. Associativity is preserved under subsets. The identity element is 0, which is even. The inverse of an integer is negative x, again, an even integer. The set of positive integers is not a group. The set 0 with respect to addition is a group. The set of positive rational numbers with multiplication is a group. Oh, I just realized y'all can't see anything. Yeah. I'm currently learning about groups. I mean, it doesn't matter if y'all can really see stuff. So the set of mappings is a group with respect to composition as an operation. in the next section. Okay. Set of all rotations is a group. So the stuff from, it's basically saying that the stuff from last section was a group. And then general linear group, we already got that. Or the way it denotes it here is GL, and then GL, N, and then F, where F is some scalar field. A group is abelian if it's commutative. A group is abelian if commutative. Okay. Okay. Theorem. Identity is theorem. Identity and identity in a group is unique. So we are, oh shoot, I didn't hit start on the thing. Okay, you know what, I'm just gonna play piano for 3 minutes. 3 minutes is how much of a penalty I'll give myself. So, because that's about how much it was. Completely forgot. This is why I shouldn't pause it. So, what is a 3-minute long song? I don't know. I don't even know any songs. Okay. So today we're only gonna that through factorization and the Euler-Totient function, which I think is a pretty good place to stop. And tomorrow we're going to go through group theory, like all of it. Maybe not all of course not all of it, but a fairly sized chunk of it. Okay. Well, basically all of it that's in an undergraduate. Well, I guess there's Galois groups and stuff, so that comes up later in the symmetry groups. Okay, never mind. We're not doing all of group theory tomorrow, but we're doing the 2 big chapters on groups tomorrow. Okay. Identity in a group is unique, and each inverse is unique. And the way you prove that is you assume different uniqueness, and you just sort of show that they are the same using associativity. Basically. Alright. So now we're going to prove that a lot of things are groups. Alright. Okay. Alright, so what are we going to prove that's a group? 1 with respect to multiplication. And times. Okay. Well, is it associative? 1 times 1 equals 1 times 1. I guess, yeah, every 1 element group is associative. Or 1 times 1 equals 1 times 1 times 1. They all equal 1. Identity is 1, so yes. Inverse, though, is there an inverse? 1 equals 1, so yeah, there is an inverse, but it's 1. And it's obviously closed. You can't get out of this set. So, yep, it's a group. And we don't have to prove that it's a group, like formally, but basically it's you just show all the axioms are true. All non-zero rational numbers. So we have P over Q, or such that P, Q do not equal 0, but P and Q are in Z. Who's here? Okay. So, and with respect to multiplication. So, all non-zero rational numbers. So if we add, we have inverses, right? P over Q. Inverse of that is just Q over P. And that's obviously in the set. So, and the identity is 1, right? P over Q times 1 equals P over Q. And then associativity. So I guess we gotta sort of show that. P over Q times, or I guess P1, Q1, P2, Q2 times Q3, or P3, Q3, that equals P1 times P2 times P3 over Q1 times Q2, or I guess this like that, times Q3. And then since the bottom is just product of integers, which integers by definition, since they're a field, they're associative, because their second operation is associative. So P 1, 2 times P3 all over Q1 times Q2 times Q3 equals P1 times P2 over P1 over Q1 times P2 over Q2 in parentheses times P3 over Q3. Done. Associative identity 1 inverses. Is it closed? Okay. Well, how would you be able to get out of it? You need to either be irrational or you would need to be 0. P over Q. When is that 0? Never. As Q gets arbitrarily large, it never reaches 0. And if P or irrational, you can't get irrational because you'd have to maybe with some kind of weird, you'd only be able to get irrational with some kind of weird infinite product. Basically, you would need some kind of weird infinite product, but since we're not dealing with infinite stuff here, it's closed basically. That's what I'm assuming, at least. Can't see the whole whiteboard? Okay, let me do that. Okay. Let's see how that looks. Yeah, you can see most of that now. Alright. Okay. So we have got closure. Alright. All rational numbers, addition. So rational numbers, addition, including 0. So 0 would be our identity, I'm assuming. 0 plus any P over Q equals P over Q. Right? Okay. Now P over Q plus, or P1 over Q1 plus P2 over Q2. You do not just simply add the top and bottom. You have to do P1 Q2 plus P2 Q1 all over Q1 Q2. This is an integer, that is an integer, so this equals Z over, this equals some P3 over Q3, so it's closed. Associativity, P1 plus P2. Do we have to show commutativity? No. No. Okay. P1 over P2 plus P2 or Q2, Q1, Q2 plus P3 over Q3, parentheses, that equals P1 over Q1 plus, parentheses, P2, Q3 plus P3, Q2 all over Q2, Q3 equals P1, Q2, Q3 plus Q P1, P2, Q3, that's Q, plus P1, P3, Q2. Okay, all over Q1, Q2, Q3. So this equals if I rearrange it properly at least. Well, you can rearrange this to P, what is it we need? We need, Q3 is going to cancel, so that's I need to rearrange this properly. This is confusing. We just need to swap these two, right? No. We swap... Basically, we put the parentheses here, and then it's a done deal. We get... this becomes P1 over Q1 plus... P1 over Q1. Oh, that's not right. That's oh no, that's not P1. P1, P2 over Q2 and Q1 plus. Oh wait, no, this is all over. P1, P3 all over Q3. Okay, I know it's a little bit crammed here. Hold on, let me move this. This is Q2, Q3. I know those look like A's. That's a Q. That's also a Q. P, Q3, it's canceled. So, how do we rearrange this? Well, that equals P1 over Q1 plus, hold up, I shouldn't have put the lines here, but P1, this is Q1, Q2, Q3. If I put these here, I get the same thing, right? We get the P1 over Q1 plus P1 P2 over Q1 Q2 plus, I guess I didn't change the order, so that doesn't change anything. Okay, I do need to change the order. If I did P1 P2 over Q1 Q2 plus P1 P3 over Q1 Q3 plus no, I don't need to change anything. Hold on. This is P1 over Q1 plus P1 P2 over Q1 Q2 plus P1 P3 over Q1 Q3. Okay, let's separate. How do I separate these though? Well, it's P1 over Q1 plus P1 over how long is the next section? Yeah, I know this section was really long. That's because you gotta hit permutations. Pretty long. Yeah, not too. Hold on, give me a second. P1, Q1. Separate these somehow. Oh, I can factor out Q1. I can factor out P1 over Q1. So this is P1 over Q1 times 1 plus P2 over Q2 plus I guess I messed something up. Maybe it was my handwriting. Or maybe it's just because it's not commutative. Or not non-associative. Whatever the case, I think I'm like pretty sure it's associative because it's a subset of the real numbers, or the rationals. Well, we already showed that positive rationals, so yeah, and it has inverses. So yeah, it's a group. Wait. No. It's not a group. What? I could have showed it. P over Q can't equal identity. Oh wait, no, it does have. Never mind. It is a group because it can. Right. P over Q. Then we have negative P over Q. That's our other element. So yeah. All right. All right. All rational numbers multiplication. No, because 0 doesn't have an inverse. 1, negative 1, negative 1, 1, and multiplication. Is it closed? Yes. What's the identity? Well, everything has an inverse. What's the identity? 1. So yes, it is a group. I didn't show it, but I just did it in my head. So the integers mod k, or mod 10, sorry, z 10k, or z over 10, or something like that. Something like that. It didn't introduce a notation for that yet, but it will, like in the next section. And yes, it has inverse. Everything has an inverse, and the identity is still 0. All right. All integers subtraction is subtraction. Okay. Yes. Because subtraction is just simply addition of negative numbers, so you just flip things around. Okay. Verify. Okay. 4 groups, and they're simple. So now we've got some better stuff. So let F denote M of R, set of all mappings. F be the set of all mappings. Let F denote M of R. Can y'all see this? Subtraction isn't associative. Oh, oh no, that's not good. I did a big oopsie. Yeah, that's the big thing about a subtraction. Has all the other properties except the most important one, which is associativity. A minus B does not equal B minus A. Right? That's like first grade math. So, it's not a group. Not a group. Can't believe I made that trivial mistake. Okay, now back to this scroll. Let F denote M R G in F, define F plus G, or F plus G of X to be equal to F of X plus G of X. Okay, verify that this is a group. So it's instead of all real mappings. So inverses. Well, what's our identity? Our identity is the zero function O of X. Because this is addition, not composition. O of X is our identity. So F minus G of X, or F minus F of X, or I guess our inverses are going to be minus F, because right, F minus plus minus F, or minus F of X equals F of X minus F of X, which equals O of X. Our oh, I proved that subtraction wasn't commutative, not associative, not non-associative. Okay, if you can't tell, I'm already getting tired. That's not an excuse, though. That's not an excuse. But not an excuse. But I'm just saying, you can tell I'm already tired. And if you spot a mistake, please correct me. I will not be mad at you. I will be mad at myself for missing it. Okay, so we got, those are our inverses. We need associativity. So what is F plus G plus, I don't know, H, or F plus G plus H of X of X. We define it to be F of X plus F, or G plus H of X plus G plus H of X equals F of X plus G of X plus H of X. Right? And since these are all real numbers, this is a real number, this is a real number. Real numbers are associative by like their definition, I guess. And this will be F of X plus G of X plus H of X, which equals F plus G of X plus H of X. Like, yeah, it's associative. So we've shown associativity, inverses, identity, closure. Yeah. Oh wow, we're at 1 viewer. That's nice. Okay. Let H, okay. Now, second example. Let H equal the set F map such that F, that has to be a typo, right? I think that is a typo. F maps from R to R, and F of X is never 0 for all X in R. Okay. So now define f g of x to be equal to f of x times g of x. Verify this operation is a group. How does this differ from the group of invertible mappings? Huh. Okay, so prove that this is a group. Okay, so define our one function. I'm gonna call it 1 of x to be such that 1 of x time 1 times f equals f of x. So that's our identity. Is there inverse? Well, since we have real numbers, yes. If we have g equals 1 over, or g of x equals 1 over x, since f of x never equals 0, we can have f of x times, or 1 over f of x equals 1. Or I guess 1 of x equals 1 for all x. That's what our one function is. Okay? So yeah, that's our g of x. So yes, there is an inverse. So we have inverses, check. Closure, and this is true because f of x is never 0. So we have inverses, identity. So actually, I'm going to put our checklist for group up here. Identity, or no, associativity. That's like the hardest or most important one to prove. Identity, or or I guess closure. Associativity, identity, and inverses. Alright, so this is good, this is good. Associativity, let's have f g of x times h of x equals f g times of x times h of x equals f of x times g of x times h of x. Since these are all real numbers are always associative by their definition. Basically, this equals f of x times g h of x. That's associative. So associative and closure. Can we ever get out of this set? Maybe. Let me think. If we had f equals like square root of x, g equals, I don't know, negative x. Would this get us out? No. Because there's a graph of square root of negative x is just something like, I think this. So it's still there. So yes, it is closed. All right. Okay. So now we gotta show that if S is a set, if the cardinality of S, the set is greater than 1, then the set of all mappings M of S is not a group. Okay. Why would it not be a group? One thing I want to say would be closure, but that's not true. That's not like the main reason. Oh wait, with respect to composition. Okay, yeah, composition. So compose two things. I think it's because, oh yeah, it's not associative. It's not associative. If you do F of G of H, no, it has to be associative because it's a category. That's like the most important thing. Oh, it's probably inverses. Yeah, it's inverses. That's why it's not a group. It has everything else though. Sorry, Canoe, not today. It's because of inverses. Inverses are not in the set. There's it's not invertible. Composition, right? Yeah. So, and it didn't say prove that there was not existence of inverses, but if there was, you basically assume there was, and you'd show that there aren't any. Okay. Okay. So these are not general linear groups. These are, okay, so G is a set of 2 by 2 matrices such that determinant set equals a set of A in M 2 by 2 such that determinant of A is not equal to 0, but it is also determinant of A is always rational. So prove, wait, does it say prove? Yeah. Prove that G is a group with respect to multiplication, matrix multiplication. Let's do a dot. Okay. Getting tired. Who knew math was tiring? Just need to chill and then get back at it. Okay. Okay, can y'all see this? Yes, y'all can. So we're proving that it's a group. Matrix multiplication is always associative. Oh, I erased the associative. So we just need to prove closed, identity, and inverse. Okay, so now so let's prove that it's closed. How do we prove that it's closed? It's matrix multiplication. So AB equals, and since this is an M2 by 2 row column, right? We'll let A. Well, hold on. A equals A11, A22, A. B equals this. B11, B12, B21, B22. A times B equals, by definition of matrix multiplication, A11, B11 plus A12 times B21, and all of these. So its determinant is in Q. So we'll have to check the determinant in just a little bit. Have to make sure that that's rational. B12 oh, wait, we can just use the fact that determinant of AB equals determinant A times determinant B. This is in Q, this is in Q, so this is in Q, so yeah, okay. It's an n by 2 by 2 with real coefficients. Okay, I didn't have to do all that. So I guess I need to write proof, basically. So part I, we know det A B equals det A det B, and since Q times is a group, we already showed that. I guess slash 0, Q slash 0 star is a group. We know that A that B is in Q slash 0. It is really nice outside, and it's also really stuffy in here. I might go outside later. So we've proved that part. So it's closed. It's in this set. So now second part, we need to show identity. What is our identity? Identity I2 equals 1 0 0 1. I mean, and or det of IT. I don't even need to write it down, but det of I2 equals 1. So det of A times I2 equals det A. Well, I don't even need to show that, but that's so A times I2 is in our. Well, I don't even need to show that. I just need to show that A times I2. Well, I2, right, is in G, because I2 is in G because det I2 equals 1, which is in Q/0. Okay. So A times I2 by definition is A. Is it commutative though? Well, let's show that. I2 I2 I guess equals A11, A12, 13, A1 R21, A22. Don't forget to eat. Does it need to be commutative? No. No, the identity does. Identity needs to be commutative. That's what I'm showing right now, is that identity is commutative. But the group does not, the matrix multiplication does not have to be commutative. So this one's true. Now I2 times A equals 1001 times A1, 2, A1, A2 equals that is A11, A12, A21, A22. So commutative identity equals A. So commutative identity, so identity is good. Inverses, well, det A is not 0, so matrix is always invertible. Since it's but how do we make sure that its inverse has det A such that they're in Q? So let's have A inverse equals 1 over A11, A22 minus, or I guess I should just put det A. 1 over det A times A conjugate. Is it conjugate? Something like that. So this has all rational coefficients. So determinant of A conjugate is rational. Determinant of A, so this is just a determinant of something that's just a product of rational numbers. I'm not going to show all the computations, just matrix stuff. I actually did take a break earlier, so that's why the speedrun time is different from the actual time of the stream. So I did take a break earlier. So it hasn't been 6 hours straight. So yeah, matrix stuff. I mean, you've got det A is a rational number, 1 over it is rational, and then you just multiply it, and then you do determinant of that, which will be in the group, or which will be in G. So G is a group. G is a group. Okay. All right. That was a good one. Oh, is it abelian? No, it's not. Not abelian. That was the last step. All right, let G denote the set of let G I'm actually not cold. I'm like boiling right now. The room's pretty stuffy. Reminds me of last year. It's because my door's closed and my room gets really stuffy whenever I keep my door closed. Usually I have my door open to keep it from being stuffy. Okay, hold on. Let G denote the set A in M 2 by 2 such that determinant A equals 1. Prove that G is a group. Prove that G star is a group. Or G dot is a group. Prove is a group. Okay. So, so prove that G is a group. You do prove that G is group. Okay, so we need to show closure. Determinant A is 1. So identity first, or actually I'll show identity first. I2, determinant of that is 1. So or just IN, whatever. So that is, so I2 is in G. Then second part, we need inverses. So determinant A is 1. Well, it's non-zero, but let's think about it. Okay, so A inverse equals 1 over det A times A conjugate. And so det A is already 1. So this is just, we have A equals A conjugate. Or it's not really conjugate, I forget the name. Basically, you in 2 by 2 cases, you swap, like you swap the C, or you have D, A, negative B, or negative C, negative B, something like that. So the determinant of this, so we know that determinant of that, determinant of A inverse is 1 over 1 times dA plus, or minus CB. Well, we know that AD minus BC, and since real numbers are unitive, this equals AD minus BC, which equals det A equals 1. The determinant of A inverse is in 1, so that means A inverse is in G. So inverses are in G. There is a window, however, I blocked them all off because the light was shining in earlier. I might do a room tour later when I finish the next this chapter. Also, yeah, I will be ending the stream after I finish this whole next chapter, and then I will be starting it up again after a quick break and like a dinner break, and I will do the next chapter for the rest of the day. till I fall asleep, basically. Then we'll start up tomorrow. So, yeah. All right. So,
Hey Jeff,
all right. Oh, I had to show that it's closed. Determinant of AB equals determinant. Yeah, this is just det A, det B. So equals 1 times 1 equals 1. So AB is always in G, so it's closed. Alright, group. It's a group. So that's cool to know. So we're almost done with this section. 6 hours in. Yeah, okay. A little bit behind. Let's see if... Okay, so we have if... So we got the last few questions. We're almost done with this section, actually. If... Let's see. A, B is a group. If you're wondering what a group is, I read the definition earlier. Yeah. All right. Is a group. Already has 2. AB. If AB is a group, if operation star is a group, or AB star is a group, what must the Cayley table be? And so A is identity. So we have A, B, B. So this looks like this, A, B, B. This should be A. B star B must be A, since it's a group. That's good to know. Alright, next question. So X, Y, Z is a group. It's the same question. X, Y, Z, X, Y, Z. X is identity. And it's a group, so we have X, Y, Z, Y, Z. It's like the if it's a group, it should be a what's it called? It basically needs to have the what's it called? Needs to have the Sudoku puzzle thing. Well, no, that's if it's an operation. If it's a group, it will be symmetric along this. X, X, and then this will be Y. Symmetric about the diagonal. Something like that. Okay. I think that's Cayley's theorem. Yes, room tour? Alright. Once I finish this section, I'm almost done. Last question. This is the last question, and then I'll do a room tour. Prove that if G is a group. Okay, prove. If G is a group A is in G, and A star B equals B for some B in G, then A must be identity. Okay. So, well, assume it isn't the identity. Well, it's because identity is unique, I guess. That's one way to say it. Assume well, since, well, I guess no, we can't use that statement because of we're assuming that left and right identities are the same. Oh, left and right identities. No, well, oh no, we don't know commutativity. Well, okay, we know A star B equals B star E, which is some other identity. Assume basically the opposite. Assume A is not identity. Then there exists some E in G such that B star E equals E star B equals B. But if we did, I mean, we could use associativity. A star B, or no, I guess we star B on both sides. We don't know it's commutative, so I don't want to use that. But let's try this. E star B star A equals B star A, right? No, I don't want to use that. AB equals EB. AB equals EB. Yeah. You know, that is true. And then you can cancel. Because there's inverses. Because there's inverses, you multiply by, or star B inverse. So now you have A star identity E equals E star E. So we have A equals E. So they're the same. Contradiction or whatever. So A is identity. Okay. Thanks for the tip. Alright. So we are done with that section. We're going to do a room tour. Alright, so we've got my computer that I'm using to stream, I've got my piano, got my drum set, and all my shirts and stuff I got for Christmas. I got a lot of shirts for Christmas. If you can't hear me, it's because the mic is over here. You got a giant style of books, Vaxay style. We've got some other stuff on the desk. Got some more clothes. Those weren't Christmas gifts. Those are just normal clothes that I haven't put away. Yeah, drum set. There's the whiteboard that I set my record on last year. There are my windows. Some other stuff. My bed. I'm using that pillow to block off light. And that's basically it. So, yeah, that's my room. now time for okay, now time for where did my notebook go? Oh, there it is. Time for permutations. So we are about 6 hours, 15 minutes in. We are on section 6. Not terrible. All right. Okay, permutations. So it's an epimorphism. Not really. Hold on. Not epi. Hold up. Permutation of a non-empty subset S is a bijection from S from S to S. So is a F from S to S. F is bijective. Also permutation theorem. So they denote it S. Okay, so theorem. Let me tilt this downward. Yeah. Okay. The set of all permutations of a non-empty set S is a group with respect to composition denoted sim S or Sn with n elements. So when S is finite, sim S, if S is finite, then this is Sn. Permutation group is called Sn. Okay. So let's see how this looks. An element alpha of Sn can conveniently be represented in two-row form as follows. We first write 1, 2, 3, 4, and below each number k, write its image, a alpha of k. So like this, we have 1, 2, 3, 4. Then we have 2, 4, 3, 1. Or no, 2, 4, 3, 1. This is a permutation in S4. Okay. So the inverse element is attained by reading, and then the identity is in Sn is 1 1 1 or 2 2 da 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 n n. Basically, they all map to itself. Identity. The inverse is obtained by reading the bottom entry. By reading from the bottom entry to the top entry, rather than so if one appears. So, 1 2 2 4 3 3 4 1. The inverse of that equals 1 2 3 4. So 1 goes to 4, 2 goes to 1, 3 goes to 3, and 4 goes to 2. Okay, so now in composing permutations, read right to left, thus okay, so some authors do left to right. So let's try this. We have 1 2 3 4 4 3 1 composed 1 4 2 1 3 3 4 2 equals, well, I mean, since they're inverses, identity, how would you do this? 1 goes to 4, 4 goes to 1, 1 1, 2 goes to 1, 1 goes to 2, 2 2, 3 goes to 3, 3 goes to 3, 3 3, 4 goes to 1, 1, or no, 4 goes to 2, 2 goes to 4, 4 4. Okay, so you're going to be hearing me say that a lot, is goes to, and there's no one watching. Great. Alright, so element S3 okay. Theorem. So what is it? Okay, so that notation is also just simply represented 1. Then we have, so will it show later notation, cycle notation later? Yeah, it will. Okay, so this notation is just simply to help, but it's meh. Okay. Okay, so it'll introduce better notation later. Or not really better notation, but the more concise notation. Alright, so now, theorem. Theorem. The order of Sn is n factorial. You missed the room tour? You can just go back a couple minutes. What are you watching? You're watching me study this book at world record pace. Yeah, I'm trying to do this whole book within 2 weeks, which is gonna be pretty hard. So right now I'm studying. I'll do some problems later on the whiteboard so you can actually see. But right now I'm studying and just writing the proofs for each theorem as it goes. So the problem with computing the number of elements is the same as computing that can be placed in n different lengths just once. That's not a proof. Come on. I guess it is. Hold on. If we begin filling in the blanks left from right, there are n possibilities for the first blank, and then there are n minus 1 possibilities for the second blank, n minus 2, and so on. And then follows by repeated application the basic counting principle. If one thing can be done R ways, after the second thing can be done S ways, then the two things can be done together R times S ways. Okay, whatever. There are, so you have 1, 2, 3, 4, 5, blank, 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 are n choices for first, n minus 1 for 2, and so on. So the total number of ways is the product from I equals 1 to n of I equals n factorial. Okay. Here's another cool theorem though. Theorem if n is greater than or equal to 3, then S3 or Sn is non-abelian. Okay, so okay, proof. Oh, come on. It just does proof by example. It doesn't really actually show it, but it just shows that you can, well, no. Proof by example works in this case because it's supposed to be for all n. But okay, yeah, I guess it works. Okay, and then alpha composed with beta equals 1, 2, 2, 3, 3, 1. Okay. All right. Thus, beta composed with alpha does not equal alpha composed with beta, so it's not abelian. So now we're just learning how to write cycle notation. So begin with 1. So 1 goes to 2. Okay, so the thing, consider this. We have 1, 2, 2, 4, 3, 3, 4, 1, 5, 5. Right? So to write this in a more concise way, we start with 1. Always start with 1. That goes to 2. 2 goes to 4. 4 goes to 1. Right. 3 goes to 3. 5 goes to 5. Identity things, so it just goes 1, 2, 4. That is how you write it. Okay. So product is usually composition. So consider we're gonna do the product 1, 2, 4 with 3, 4. Okay, begin with 1. 1 goes to 1 in this case, or 1 goes to 2 in this case, because the other thing. 2 goes to 4, but 4 goes to, so gives 4 goes to 3, right? And this one fixes 3. So 4 goes to 3, and then 4 go, and then 3 goes to 4, which goes to 1. Okay. So example. So cycles are disjoint if none of them are the same. Okay, so if A1, A2, all the way up through AN, and we have B1, B2, all the way up through BN, BM are disjoint if AI does not equal BJ for all I and J. Okay. Okay. So, and that's a problem. Or it's not a problem, but it's going to be a problem to prove that 6.15 prove disjoint cycles commute. So yeah, I feel like this is where things start getting a lot longer. Problem sets. But things get shorter after the equivalent stuff. Pretty easy. Just more set theory, modular arithmetic, primes. we're trying to finish up through section 13 today, which is gonna be tough. Still have, we're about halfway there. Well, a little bit more than halfway. So yeah. Okay. So any permutation of a finite set is either a cycle or can be written as a product in the inclusion or omission of one cycle. Okay, this can be done in only one way. Okay. And the proof is apparently trivial. Alright. There's a Cayley table. Okay, so now let's do the problems. We can do this. These aren't too bad. Alright. So at around 7:30, 7 hours 30 minutes, let's try to move on to the next section, which is subgroups. Subgroups. Yep. So it took me about 30 minutes to learn about cycles. It's pretty impressive, not gonna lie. Oh my goodness, I'm so tired. Like, jeez. Need more people in chat. That's what I need. Invite all your friends. Come have a jolly good time. Alright, so it begins off easy with this baby cycle notation. Why do I call it baby cycle notation? Because it's just meant to keep things easy. 2, 4, 3, 3, 4, 2. Just meant to make you comfortable. Beta equals 1, 3, 2, 1, 3, 4, 4, 2. Alright. So, we've got, okay, so now it wants us to compute beta composed with alpha equals, so we have 1, 2, 3, 4. 1 goes to 1, and then 1 goes to 3. 2 goes to 4, and then 4 goes to 2. 3 goes to 3, and then 3 goes to 4. 4 goes to 2, and then 2 goes to 1. Okay. What does it want now? Alpha composed with beta equals 1 goes to 1. Oh no. 1 goes to 3, 3 goes to 3. Or 2, 3, 4, 3. Did I do this backwards? No, I didn't. 3 goes to, oh, 1 goes to 3, 3 goes to 1. Yeah, or no, 3 goes to 3, yeah. Okay. Then 2 goes to 1, 1 goes to 1. Then 3 goes to 4, 4 goes to 2. And then 4 goes to 2, then 2 goes to 4. Okay. Alright. Did I? I didn't split, of course. Okay. Well, that's not good. I keep forgetting to split. Okay. I should have split a long time ago. Okay. C. Alpha inverse equals 1 goes to 1. 1, 2, 3, 4. 1. 2 goes to 4. 3 goes to 3. And 4 goes to 2. Simple. Can y'all see this? Yes, y'all can. Alright. Beta inverse equals goes 1, 2, 3, 4. 1 goes to 2. 2 goes to 4. 3 goes to 1. 4 goes to 3. Beta inverse composed of alpha inverse, which equals 1. Okay. Beta composed with alpha inverse, so alpha inverse, we go 1 goes to 1, so 1 goes to 2. 1, 2, 3, 4, you have 2. Alpha inverse 2 goes to 4, 4 goes to 3. 3 goes to 3, 3 goes to 1. 4 goes to 2, 2 goes to 4. F. Alpha inverse composed with beta inverse equals so 1 goes to 2, 2 goes to 4. 1, 2, 3, 4, 4. 2 goes to 4, 4 goes to 3. 3 goes to 3, 3 goes to 1. 4 goes to 2, and then 2 goes to 4. Okay. And then G. This is a lot of parts. Beta composed of alpha inverse. That equals, we've got beta composed of alpha, all inverse, so this inverse is 1 goes to 2, 3, 4, 1 goes to 4, 3 goes to, 2 goes to 2, 3 goes to 1, and 4 goes to 3. And then H, alpha beta inverse equals yeah, this is fun. Really fun. So what's my favorite cereal? Not, I read that wrong. Cereal. I haven't had cereal in a while because milk makes me sick. Sadly, I love milk, but it makes me sick. I used to love Cheerios, but that would make me the most sick whenever I had Cheerios. Cinnamon Toast Crunch is always solid, but it's not like amazing. Same thing with Lucky Charms, although there's always that guilt factor when eating Lucky Charms because they're so unhealthy for you. But I would say in terms of pure taste, I love Lucky Charms. Cinnamon Toast Crunch though are always solid and they're easier to convince your parents to buy. I mean, they're still probably just as unhealthy as Lucky Charms. And then there's I guess that's it. Yeah, Lucky Charms, because, not only are the marshmallows tasty, but, the cereal itself is really tasty. Like even without the marshmallows, the cereal is pretty solid, and the texture also is pretty good. I like texture in my cereal, so yeah. There are a lot of other cereals that I haven't really tried just because those three are just like so solid. Like I don't even really bother to try all the other good ones, like Reese's Puffs or Cocoa Puffs or like Fruit Loops. Well, I guess I've had Fruit Loops. They're basically Cheerios. Okay, beta composed output composed of beta information 1, 2, 3, 4. We have 1 goes to 3. No, 3. 1 goes to 2. 2 goes to 3. 3 goes to 1. 4 goes to 4. Boom. Alright, that was the first question. Took us like a decent while. Repeat problem 1. No thanks. Alright, write each of the following as a product of disjoint cycles. So we have, we're just learning to write in cycle notation. So this equals, oh wow. Okay, my microphone fell. So that's nice. So let me quickly fix that all up. So we put the microphone where? Put that. Oh, we put that like this, didn't we? Put the microphone. No. Okay. Let's hope that doesn't fall. All right. Yeah, that did too. That scared me too. I was just like, "Oh, what? Why did it fall? Let's make sure it doesn't fall again." I mean, okay. Alright, so start with 1. 1 goes to 3. 3 goes to 6. 6 goes to 1. Close. 4 goes to itself. Close. Or I guess start with 2. 2 goes to 5. 5 goes to 2. Then 4. So yeah, that's it. Okay. So we got 1, 2, 1, 3, and 1, 4. This will equal, so 1 goes to 2. 2 is omitted, so start with 1. 1 goes to 2. Wait, hold on, how does this end? 2 goes to nothing. 2 goes to 1, which goes to 2 goes to 1, and 1 goes to 3, which goes to 1, which goes to 4. Right? I think I should check the answer for that. Very few actual answers in this book, but I think there should be some for this one. Yeah, I'm good. Wait, 1, 4. Okay, hold up. I need to Oh, because it ends at 4. Ends at 4. Go until it ends. Okay. Okay, so here's how it works. 1 goes to 2. 2 goes to 1. 1 goes to... And so then you start here. 1 goes to 3. 3 goes to 1. 1 goes to 4. I think that's how it works. Or 1 goes to 4. 4 goes to 1. 1 goes to 3. I guess I was reading it backwards. 1 goes to 3. 4, 2. Did I get that right? Yeah. I did get it right. Okay. Yeah, I know, right? Math speedrun is amazing. Someone knocking?
Food?
I'm good.
Alright, let us know.
I'll let you know. Alright. 1, 3. Inverse. 2, 4. Times 2, 3, 5. Inverse. So first I need to calculate what this inverse is. So it's basically, hold on, 1 goes to 3, 2 goes to 2, 3 goes to 1, 2 goes to 1. Okay, so then 1 goes to 3. Okay, so that's very useful. The inverse, you just swap things around. Okay, so that becomes 3, 1, product, 2, 4, composed with 5, 3, 2, or do you swap things? Okay, hold on. I think you just, I don't think you swap things. 3 goes to 5, so 5 goes to 3. So 2 goes to 3, 3 goes to 5, so 5 goes to 3. Special guest. I am a math tutor sometimes. Well, pre-COVID, I used to tutor a lot more, but now it's a lot harder to get an actual job. So I just sort of do private tutoring, and I don't advertise that much, but I probably should. I could make a decent amount of money from it. Even if it wasn't, I wouldn't really care for the money. I just want to help people with math. 2, 3, 5. Let me write this down. Goes to 1. 2 goes to 3. 3 goes to 4. Or no, 3 goes to 5. 5. 4 goes to 4, and then 5 goes to 2. Okay, so the inverse would be 1 itself. 2 goes to 5. 5 goes to 2. 5 goes to 3, and 3 goes to 2. Okay, so you just swap things around. Okay. All right. So now, how do we do this? This equals. I feel like I should start with 1. 1 goes to 3. 3 goes to 2. Which goes to 5. So start with 1, goes to 2, goes to 5, which goes to 3, which goes to 1. Okay, no. 1, start with 1, which goes to 3, which goes to 2, which goes to 5, 2 also goes to 4. Okay, I don't know how to do this. I'm assuming, since Sn is associative, let's do these two first. So since it's associative, we've got 3 goes to 1. That's a product of disjoint cycles. So let's do the non-disjoint ones. Since it's unique, yeah. We have 3, 1 times 2 goes to 5. So start with 1, that's omitted. 2 goes to 5. Goes to 5. Or no, 2 goes to 4. 2 goes to 5. 5 goes to 3. 3 goes to 2, which goes to 4, I think. And then these aren't the same. So then we got start with 1, which goes to 3, which goes to which goes to 4, which goes to 2, goes to 5. Let us see if we are correct. What's up, y'all? Almost 7 hours in. Amazing, isn't it? Hey, I got it right. Big flex. Got it right. Wow. I'm not quite feeling comfortable with products yet, but I'm feeling pretty good. So let's do this last one, and I think I'll be good. 2, 4, 5. 1, 3, 5, 4. 1, 2, 5. Okay. Okay. Yeah, all those problems are easy. I think I can catch up, like, easily. Like, I think I can definitely get all the things I wanted to get done today. Well, here's the thing. I spent the first 5 minutes setting up my setup, so, yeah. Trying to make sure it was all good. I still am trying to figure things out, but, you know, we working through it. Yeah. So, man, I am so tired. I love this. Yeah. This is great. My brain is dead, and I don't know what to do. But, you know, we're just gonna do it. Start with 1. Where does 1 end up? Goes to 3. 1 goes to 2. 2 goes to 1 goes to 2. Associative. Okay, I'm still confused as to how to do products. Disjoint cycles. They're not all disjoint. Come on. Okay, let's just do 2, 4, 5 times. Let's just do this product first. 1. Where does 1 end up? 1 goes to 2, which goes to 5, goes to 4, goes to 3, which goes to 5, which goes to 4. Wait, hold on. What? Goes to 5, which goes to 4. That's not right. 1 goes to 3. Hold up. Oh, pairwise or disjoint. Yeah, pairwise is where you. Okay. So this is tough. Oh, we made it to 7 hours. We made it to 7 hours. Yay. I'm on section 6, so it's about an hour per section. That'll be 50 hours if we did all the sections I wanted to. So, yeah. It's quite a while. One, two, one goes to two, two goes to five, five goes to four, four goes to one. So where does three end up? What? One goes to three, goes to five, which goes to four. Oh, I think I have to. How do I do this product? I did. 3, 1, okay. And then I did 2, goes to 5, goes to 2, which goes to 4. Okay. So 1 goes to 2, goes to 5, goes to 4, goes to 1. Close. 3 I guess goes to 5, which goes to 2. Which goes to 1. 3, 5, 1. Now we do 3, which goes to 5, goes to 4, goes to 1. That does not help anything. Well, let's see how I did composition before. Oh, yeah. So let's just write everything in baby notation, and maybe that'll clear some things up. 1 goes to 3. 3. 2 goes to 2. 3 goes to 5, and 4 goes to 1. Oh, 5, and then 5 goes to 4. Times composed. So we're doing this in big parentheses. 1 goes to 2, 2 goes to 5, 3 goes to 3, 4 goes to 4, 5 goes to 1. Okay. So composing this, we get 1, 2, 4, 3, 3, 4, 5, 5, 2, composed with 1 goes to 3, and 3 goes to, 3 goes to 3, and 3 goes to 5. So, let's go with 1. 1 goes to 2, and 2 goes to 2. 2 goes to 5, and 5 goes to 4. 2, 3, 4, 5. 4, 5. Exactly. Math is entertaining. It's the most entertaining thing ever. I'm telling you, math is like. That's what math is. That's what math is. That is the sound of everyone who does math. One, two. Hold on. 1 goes to 2. Okay. 2 goes to 2. No. 2 goes to 5 and 5 goes to 4. Okay. 3 goes to 3 and 3 goes to 5. And then 4 goes to 4. Okay. And 4 goes to 1. Okay. 3 goes to 1, and 1 goes to 3. Boom. Alright, so then this just equals in big notation is going to be, I'm not sure if y'all can see this. It's on this lower part of the board. 1 goes to 2, so hold on, 1, 2, 3, 4, 5. 1 goes to 2, and then 2 goes to 4. 2 goes to 4, and then 4 goes to 5. 3 goes to 5, and then 5 goes to 2. 4 goes to 1, and then 1 goes to 1. 5 goes to 3, and then 3 goes to 3. Oh, 5 goes to 3, 3. Okay. So, this equals, in notation, 1, 4, 2, 5, 3. Okay. I did it. So I guess that's the easy way, is to do big notation instead of trying to do all the little notation. Okay. Now let's on to some proofs and stuff, and then we'll be done with this section. After that, we're on to subgroups. Subgroups. We're getting places. That's the thing I like. There's so much more to abstract algebra, but I like that we have gotten some places today. We learned a lot. We made friends along the way. Okay. Alright, write S4. Okay, so 6.5. We've got write all elements of S4, both in 2 rows. So we have 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 1, 2, 3, 4, 3, 4, 2, 1, and 1, 2, 3, 4, and 4. Oh wait, no. This would be 1, 2. N factorial. Wait, hold up. 4 factorial is 12. There's like 3 things to write. 4, or there's like 12 things to write. 4, 1, 2, 3. You know what? No thanks. Too long. Didn't read. Basically, how many elements of S4 are their own inverse? Well, obviously the identity, so it's at least 1. But also, I want to say along the diagonal, so it's going to be 4. 4 things are its own inverse. Okay. My hands smell like marker. It's not a good smell. Am I doing this again tomorrow? Yep. 7 weeks. Not 7 weeks. Oh my gosh. I would not be able to handle that. No. Probably 12 days. 12 days is how long it'll take. So how many elements in S3 map 3 to 3? well, how many elements in Sn map n to n. Well, there's n factorial. It's gonna be n minus 1 factorial because you keep one fixed basically, and you can permute all the others. So n minus 1 factorial. So write a1, a2, dot dot dot, ak inverse in cycle notation. So let's go ahead and do a1. That's nice. Thank you for watching. I know it's not the most exciting thing. So you just sort of flip-flop things around, right? This inverse equals, so a1 goes to ak. You just swap the endpoints. That's cool. You write theorem? No thanks. Show that every element of Sn is a product of two cycles. Is a two-cycle. Also called transpositions. So we're just gonna do that in the next section. There's just more stuff with cycles. Man, we're gonna get there. We're gonna get there. We're gonna learn abstract algebra. Just that there's so much to learn. That's the crazy part. Tomorrow I kind of want to start with a review session, but I'm not sure if I have time for that. I think there's enough that will be reviewed. Okay, so transpositions if complete. Okay, if G is an operation star, if and only if for all A. Okay. Prove. Okay, so we gotta prove that prove that S3 is non-abelian. Yeah, non-abelian. There is a lot of math. It's insane how much math there is, like past all the stuff you learned in high school. What am I doing? I don't know. Okay, prove that S3 is non-abelian. Okay, well, the alpha and beta be S3. Alpha equals 1, 2, 3, then some number a, b, c, alpha not equal beta, beta equals 1, 2, 3, well, I guess ABC. I guess, well, the proof is that you just show that there exists an element where it's not true. So, like, let's just do 3, 2, 1. And 2, 3, 1. So alpha composed of beta equals 1 goes to 3, or beta of 1 goes to 2, 1, 2, 3. 1 goes to 2, and then 2 goes to 2. 2 goes to 3. 3 goes to 1. 3 goes to 1, and 1 goes to 3. And beta composed of alpha equals alpha 1 to 3. 1 goes to 3, and 3 goes to 1. So it's already not different. So we've proved by counterexample. So that was pretty easy. Now it wanted me to prove a more general statement. Okay, we are almost done with this section actually. Can you believe it? There is a seemingly infinite amount of math, and no one person knows all of it. But there are people who know a good chunk of it. My hands. Oh wow. Getting dark. Okay, I need to focus. Hocus pocus. Prove that the group in example 5.8 is abelian. We already did that. Not abelian, I guess. It's more of a review problem. Okay, consider the following for the Cayley table, and then we'll do one last problem. Oh wait, no. Okay. So we have a Cayley table. No, we don't. Oh, this is the last problem. Okay. Oh, okay, so we have, assume that alpha and beta are disjoint cycles of Sn. So alpha, beta in Sn, where alpha equals A1 through AK. A1, A2, AK. Okay, and beta equals B1, B2, all the way through BK. Alright. Assume that alpha, beta are disjoint. Okay. Compute. Okay, so A, just compute alpha composed of beta of AK. Okay, I mean, I guess when we do that equals, well, AK goes to A1, goes to A2. So for beta of AK doesn't exist, so it goes beta. Well, it's not commutative. So, well, first, yeah, beta. We have alpha goes to A1. So, of AK, how does that even make sense? Okay, so alpha and beta. AK goes to A1. So, and since they're disjoint, it's just going to be A1 or AK A1 dot 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 AK minus 1. Yeah, I guess this is like the best I can guess on this one. I have no clue what this is asking. I really don't. Like, I don't know what this notation means. Maybe I'm just too brain dead to understand what it's asking, but yeah, I'm just gonna move on to the next section. So we'll go ahead and split here, and I'm gonna use the restroom. Yeah, so let's go ahead and split and pause. I'm gonna use the restroom, take a quick break. as you can see, there's a lot more to go. If you want to see how much more to go to this, let's see. We're barely on subgroups, and there are all these sections. No, not really. Not really. Okay. Yeah, look at all these sections. They're so... How do I... Okay, I'm gonna go ahead. And start... Oh, I'm trying to get this right. This scroll wheel is hard to work with. Yeah? Yeah, I'll just start here. Okay. So, subgroups. Subgroups. Alright, what is a subgroup? Alright, definition. Kidding me? A subset H of a group G is a subgroup if H itself is a group with respect to the operation on G. Alright, so alright, notice that if G is a group with respect to operation star, H is a subgroup, and A, B, A star B, so it must be closed. Particular A star H, yeah. A group is a subset. Okay. Alright, so any group is a subgroup. There is no symbol for subgroup. That is annoying because there's a symbol for normal subgroup. I guess most useful things are normal subgroups, so that's why E is a subgroup of G. Okay. Let G be a group with operation star, and let H be a subgroup of G. If F is the so we're trying to prove so lemma. If F is identity of H and E is identity G, then F equals E, and then part B, A and B, if A is in H, then A inverse in H equals A inverse in G. So the proofs are, let's see, what do we got? We got F star F equals F. Therefore it's inverse. F inverse. We'll see. Alright. Okay, that's smart. So F star F equals F inverse. Or F star F equals F. So yeah, you do that. Okay, that's pretty good. So now, theorem. So H is a subgroup. A subgroup of G if and only if A, H is non-empty, B, closed, so if A is in H and B is in H, A star B is in H, and C if A is in H, A inverse is in H. Okay. So proof. So they need to show that identity. Oh, okay, yeah. Identity has to be in it because A star E equals E. Or no, A star A inverse is E and A star B has to be. Okay, yeah. So that's basically how you prove it. Okay, that's pretty cool. So a transposition (7 minutes 30 seconds) or 7 hours and 30 minutes. Oh god. We are working. Just haven't had much caffeine today. I wonder if there's any downstairs. Going to sleep's gonna feel so good. I wish I could have worked 16 hours today. Ugh. This is really tiring. Ugh, okay. I just spent a minute just ranting about random stuff. Okay. Back to work. Okay, hold on. a 2-cycle. Without transposition, 2-cycle in Sn. Okay. We may need either an even number and an or an odd number of factors. We define a permutation to be odd or even according to whether it be written product of even number of terms. So an even permutation number of 2 cycles is even. Odd permutation number of 2 cycles is odd. So, basic proof that what's it called? Any representation of an even cycle will be even. Okay, it'll always be even. It'll be proved. So theorem. The set of all even permutations in Sn forms a subgroup of Sn for each n greater than or equal to 2. This is the alternating group denoted AN. The order of AN is 1/2 n factorial. And since, yeah. Okay. So I guess proof that it's a subgroup, I guess. Identity in AN is 1. Equals 1, 2, 1, 2. So to prove it, you have to, man, a lot of these proofs are like unfinished, but it's even permutations. So it can be written as even. Okay. So apparently it has applications in symmetry and combinatorics. Interesting. All right. So now let's do element-wise invariant. Okay, hold on. What does this mean? Hold on. Assume G is a permutation group. Okay, assume G is a permutation group on a set S, and that T is a subset of S. Let GT equal alpha in G such that alpha of T equals T for all T in T. That sounded weird. Okay. What does that mean? Hold on. We say that the elements of GT, leave T element wise invariant. Okay. So this is more of an example. How many problems are there? A lot. Okay. Oh boy. Help. I'm just kidding. I can do this, just I'm tired. I am. Do I give up now? No. What do I sound like? A giver-upper? We've just got to do all of these problems. But hey, once we finish all these... Okay, the next section isn't that long. Once we're done, we will take a good, decent break. Wow. Yeah. And then I'll come back and do all this number theory stuff. Man, I am so tired. Like, I'm sure y'all can relate how doing math for 7 hours straight would leave you really tired. Okay, so one last theorem. Okay. If G is a permutation permutation. So yeah, we've learned our first two simple groups, two sets of simple groups. We've got cyclic groups of prime order and alternating groups for a greater than 5. Those will probably be the only two that we learn about that I learn about for a long time, because the other ones are very, very, very complicated. Well, I kind of know a little bit about the monster group because it's fun to learn about, but yeah, all the other ones, the groups of Lie type, are very, very complicated. I am not into Lie algebra yet. Okay. Permutation on S. If G is a permutation group on S and T is a subset of S, then GT and GT, hold on, what is the difference? It's image of T, okay. Okay, yeah, image of T. Okay. GT are subgroups of subgroups of G. Also, GT is a subgroup of G image T. Proof by applying identity mapping, non-empty. Set. Oh, it's GT non-empty. Oh. Yeah. Okay. Okay. I can't sing. I Yes, I know. Am I okay? No. I'm not. But I'm fine. Hey, what? No. I shall get back to work. I don't want to take a nap or go to sleep. Just not do it. No one says I have to keep doing this, but I do. I have to, or I don't have to, but all right. Time for problems. Alright, decide if each one is a subgroup of S4. So we got A. Got 1, 2, or no, 1, 3, 2, 3, 4, and 1, 4, 3. So, is it a subgroup? We have the identity. Well, yeah, it's non-empty. But are there inverses? Well, what's the... These have to be inverses of each other. One goes to 3, 3 goes... Okay. Yeah. Let's see if there are inverses. These have to be inverses of each other. So is it true? 1, 3, 2, 3, 4, 4, 1. Closed with 1, 4, 3, or 2, 2, 3, 1. 4, 3. So let's see. We get 1 goes to 4. No, 1 goes to 1 goes to 4. 4 goes to 1. 1 goes to 2. 2 goes to 2 goes to 2. Yeah. 3 goes to 4. Or no, 3 goes to 1. Or 1 goes to 3. Yeah. Okay. So they're inverses. So yes, it's subgroup. Okay. There's inverses. Yeah. Associativity of always hold. Okay. So basically, first off, they need the identity, but if they aren't inverses of each other, not a subgroup. If they are, then yeah, they are a subgroup. Okay, that's fine. Same deal. Okay, this one's important. So S equals 1, 2, 3. And our group G equals S3. GT, so GT by definition was we set alpha in G such that alpha of T equals T for all T in T, and then G T with that is just alpha in G such that alpha of the image of T basically equals T. Okay. I'll get energy someday. But like right now, it's just not feeling it. I'm not feeling the energy. Okay. G, so GT in this case equal alpha in G, which is S3. So that alpha of T equals T with all T T. T then. S and T. S. Oh. Into S equals oh, in each case, okay. A T equals 1. Okay, so such that so G of T or GT equals alpha in G S3 such that alpha of T equals T for all T. Okay, well, what is alpha? I guess the permutation group. So it's just hello, help. No, I'm fine. I'm saying that because I'm tired. What if I got food? You know, I've just been sitting here banging my head against the wall because I really need some fresh air. So, we're not ending the stream yet. But I really need a break, like an actual break. I mean, I was gonna do one after a little bit longer, but I just can't make it. So, yeah. Pausing here. I'm not ending the stream. I'm gonna end the stream once I finish the next 2 sections. Then I'll end the stream, and then I'll restart again. All right. So let's pause. And yeah, let's just take like a 15-minute break. That shouldn't be too bad. yeah, the memories are coming back with this. I'm gonna quickly erase everything just to just so I can eat, chill, read the next section maybe. See what that's all about. Groups and symmetry. Yeah, maybe I can just relax. You know? Just relax. Not too bad. Not too bad. Man, oh man. Yeah, I'm just eating right now. I'm eating too fast. Hello, Nomar. I'm just eating right now. The food's a little spicy. So, I gotta drink some water with it too. Man, I just need to. I'm doing alright. Just needed to take a break. Well, I'm just trying to eat right now. I will say that eating is actually taking a bit of energy because it's spicy food. Might want to grab some eggnog. You know what, that's a good idea. Grab some eggnog. But you know what I'm doing? I'm gonna grab some eggnog and you know, I kind of just want to chill here for a little bit. I mean, I still got to do all the number theory stuff. But hey, chilling is nice. What is it? I got to get all the way up through all those stuff. Which should be quick, but at the same time, might take a little bit. I've got, wait, hold on. 1, 2... After these 2 chapters, which will probably be around 8 hours, 30 minutes, and maybe a little longer, I'll be maybe around 9 hours. I'll stop the stream, or 9 hours of the speed run. Stop the stream, and then I'll go ahead and what's it called? Restart. And see, I've got 1, 2, 3, 4, 5 sections. I think I can do all those pretty quickly. 45 minutes each. 45 minutes each. It's basically what? It's almost 5 hours. Well, not really. Nowhere near. Well, it is near 5 hours, but it's more like 4 hours. Yeah, I don't like that my food got cold really fast. Okay. I finished. Am I attending college? No. I'm still a high school student. Well, I technically go to a college for some classes. Or not really some, just basically all. But like, I'm not really a college student. I guess technically I am a college student because I don't really do any more high school classes. Someone's calling me. Hello. Do you see I'm streaming? I'm streaming. Yes. Math. Yeah. 'Cause I want to flex my giant PP. I mean, I'm currently just relaxing right now because I fried my brain. So no, don't want to play Among Us. I mean, I do want to play Among Us, but I don't want to play it on stream. It's boring. Okay, no, I have done a lot of math. I've done a lot of math. Okay. And I'm gonna get back to it when I get back. But yeah. Well, 7 hours if you look at the timer. Or almost 8 hours. Setting up my stream and also taking a piano break. Well, it was spread out throughout the time. Like, I took multiple breaks. What do you mean, why though? you to flex. Show how strong I am. Which isn't really that strong because I'm already mentally fried. Well, as in, I still have like 12 more days of this to do. Because, did you not see this name of the speedrun? Yes. Abstract algebra is usually a 2-semester course. So I'm condensing. What? No, I'm learning it. Yeah. On the first day of Christmas, true love gave to me. Because I'm smart. Yeah. What's not smart about it? Yeah, that's true. You beat me. Well, no. Well, it's because I'm on Christmas break and I don't have anything else to do. So. What do you gotta say to that? What do you gotta say to that? Oh, I said it because it's Christmas break. I got nothing else to do. Like, what else am I gonna do? I mean, playing Among Us is fun until the 3rd game. Oh. Well, yeah, because someone. Yeah. I'm in my room. No. I'm using the laptop. Because my computer's downstairs. I'm using the laptop. No. They're just like impressed that I'm still going. Which, I mean, I'm technically not anymore. Well, I will. I'm gonna be going until I pass out. Just to see how strong I am. Nothing. I got some clothes from Walmart and a charger because my other one broke. What? What'd you say? Yeah. Yeah, we had Christmas. Alright. Alright, well, I'm gonna hang up now and get back to work. Alright, I'm getting back to work, y'all. But I will say, this is a lot more boring than I anticipated. Oh my god. Like, I at least want to do something else with my day. Holy. What if, instead of 12 days, we just keep it to, try to make it a bit more slow. No. Well, yeah. How about I end the stream after chapter 3? Yeah. Yeah. Okay. Alright. So find a subgroup wait, what? Oh, no, I'm not doing that question first. I'm doing a 2.10. Okay, 2.10. Let F. Oh, let me start the thing again. All right. Let F denote n of R let H on as in problem 5.13. What was 5.13? Oh yeah, made into a group F plus G of X equals F of X plus G of X. Okay. Alright. And prove that H, so H, let H equal the set F in F such that F of X is in Z for all X in R. Okay. So okay, yeah. Okay, so prove that H is a subgroup of F. Okay. Prove H is a subgroup so inverses. You inverse. You inverse. And closed. Okay. So say this is closed. Let's prove closure. So F plus G. Well, first off, it's non-empty because 0 of X equals 0, which is in Z. So it has identity, but it's also non-empty proof. And then part 2, we gotta prove that. Yep, I love anime. Anime is amazing. Wish I could draw my own anime girls. All right. So f minus so inverse f inverse equals minus f. So f plus minus f of x equals f of x minus f of x, since f of x and is in z. Well, I don't really have to prove. I don't have to say anything. Equals 0 of x. So it does have inverses, and minus f of x exists because z f of x is in z, and additive inverses exist for all a in z. Okay, so now we have to prove closure. So let's just take two elements, f plus g of x equals f of x plus g of x, since c is closed, f of x plus g of x is in H. So in H. So negative f inverse is in H. Thus, H is a subgroup of F. Proved. 8 minutes. Yep, we're 8 minutes in. That was all one problem, by the way. Crazy, huh? Okay. Find the elements in A4. Find, or not really find, just list A4. So that's the alternating group with 4 elements. I wanna just look that up because I wanna see how they generated it. So all even permutations. On. I really don't get exactly what they mean by that, so I'm just gonna look it up. What is it? one line notation. Okay. So we have, it goes 1, then we have 2, 3, or 1, 2, 3, 4. We have 2, 4, 3. Then we have 1, 2, 3, 4. Then we have 1, 2, 3. Right, and 4 just maps to itself. And 1, 2, 4. And then 1, 3, 2. And then 1, 3, 4. And then 1, 3, then 2, 4, and then 1, 4, 2, and that's it. No, it's not. We have 1, 4, 2. We have 1, 4, 2, 3. 1, 4, 2, 3. We have, that's it, or 1, 4, 3. There we go. So those are all the elements in the alternating group of 4 elements. Alright. Okay. Alright, consider M2Z. Consider the group M2Z alright. Prove, is it prove? Yeah, prove that the set of diagonal matrices form a subgroup okay, so integer coefficients with 2 by 2 matrix. So we need to prove non-empty. So we can just show identities in there. So identity I2 equals 1, 0, 0, 1. I2 is in, yeah, just gonna call it H, or I'm gonna call it D for diagonal. Okay, non-empty, closure. And I'm guessing it's with respect to addition. It's the operation. Okay. So A plus B equals A11 plus B 11 plus we have blah 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 blah. Since Z is closed, A plus B is in D. Oh wait, yeah, this is 0. This is 0. Is in B2 plus A2 B22 plus A22 or whatever. AB is in D, right? And now we need to show inverses. So minus A. Oh, no, identity is a 0 matrix. I just realized. Hold on. Yeah, we're not working with multiplication. So I'm going to call it 0. And 0 is in, or not R, D. Okay, A minus A equals A11 minus A1, 0, 0, B22 minus B22, which equals, not B2, A22, A22 minus A22 equals 0, 0, 0, 0 equals 0. So, identity. And then we have, and this is true, we can do this because for all x in Z, there exists a negative x. Okay, and that proves it. Okay. So, it's a subgroup. What was the second part? Find a subgroup containing only the 0 matrix. Okay, now we do this one. Find a subgroup of Q with plus that contains Z, contains Z, but is different. Oh, this is easy. From Q and Z. Okay, this is easy. Just multiples of 1/2. Or I guess it's more of a sequence, but set. Or I guess, yeah. S equals n over 2 from n equals negative infinity to infinity. And it's an infinite set, but because it has to contain Z. Well, yeah, n over 2. Now we have to prove that this is a group. Well, a subgroup. So, first off, non-empty, 0's in it. 0, take n equals 0, and it'll equal 0. So yes, 0's in it. 0, and that's the identity. Inverses, negative n, is in it because this is just from on the range of Z. So negative n must exist because n is in Z. I guess a better way to put this sequence is just for n in Z and then S does not equal Z because you know, 1/2 2n 2k plus 1 not in Z. Okay, so it's different. S not equal to Q because what is it? N over M, where M not equal 2, or I guess bigger than 2, not exist. And then what is it? So we have this, yeah, negative n must exist because that, and then okay, I think we're getting somewhere. Okay, what am I doing? Yeah. So we got all this. What was the last thing I needed to show? This was kind of unorganized. 0, inverses, closure. Okay. So take n1 over 2 plus n2 over 2 equals n1 plus n, or 2n1 plus, or I guess equals n1 plus 2 all over 2, which is in S. So, yeah. Because Z is closed. Yeah. Alright. Okay. Okay, this is a good one. Prove that if H and K are subgroups of G, then then H intersect K is a subgroup of G. So first we have to show non-emptiness. Well, E so proof, I guess. E is in H and E is in K, so E is in H intersect K, thus non-empty. Okay, that's part I. part 2. We gotta show inverses, or no, what? Closure. So let's show closure. So operation star. So let x, y be in h intersect k. X star y. Well, so x is in h and x is in k, and y is in h and x is in k. Well, I guess I should try to compute like so, and y is in k. So if we have, and then I guess since h is a group, h is closed. Since k is a group, k is closed. But so that'd be two. That's two cases. What are the cases where they intersect? Why is it that it's closed and they intersect? Oh, because they're part of G. Okay. So there's subgroups. So H and K are subgroups. Okay. So H intersect K. Okay. H okay, K. So H is in, so, and then since H is closed, X star Y has to be in H. But since K is closed, oh, X star Y is in K. Thus, X star Y is in H intersect K. And then inverses, so inverses would be I guess X inverse, but you know that E is in it. So we're trying to prove that there exists a Y in H intersect K. Well, let X be in H intersect K, since, oh yeah, X is in H, negative X as in H, But how would I show that that's in the intersection? Well, since H is closed. Well, no. Yeah, okay, proof by picture basically, right? This is H, this is K, they're all in G, right? This is their intersection. I'm not sure if y'all can see this properly, but I'm drawing it over here. This is like inverses, right? But I'm trying to show that these are all the same inverses from over here. So instead of using negative x, let's just do there exists a y in H such that x star y equals k. Equals E. But if x is in H, x is in H intersect K. No, it's not. No, it's not. I just stated something wrong. Okay. Every element of H has an inverse, right? How do I prove that of the ones that overlap, that they're still in the overlap? Well, you know that it's closed, okay? I mean, proving contradiction wouldn't help. In A, H intersect K, we'll try to prove there exists a y such that x star y, or y in H intersect K such that x star y equals E. This is what math comes to these days. All this jibber jabber. Want to show there exists a y in H intersect K such that x star y equals E. Okay. What does that even mean? How do I show inverses? They're subgroups. Okay, so they have inverses. So, x is in H and x is in K. Let y be the inverse of, I guess I should say in K, without loss of generality, let y be the inverse of x in H. How do I show that this is also in K? Well, H is in x intersect K. I guess I shouldn't say without loss of generality. But, okay, since the inverse is unique, since x is in K, y there must be inverse of x inverse y in k, or I guess y k. I'm gonna call this yh. But since inverses are unique, yh equals yk. There we go. Prove it's a subgroup. I like that. That's a good one. Okay. So this is more of a review problem. Oh, it's good. Okay, yeah. Okay. So this one, prove that if G is a group with identity E, oh wait, no, that's a different one. With operate, okay, is a group, and H is a subset of G, then H is a subgroup if and only if A, H, if and only if H is not equal to the null set, and if A is in H and B is in H, A star B inverse is in H. So that's a lot to prove. So this is a big proof. This is 7.22. So first we have to go this way. So first we assume that G is a group and H is a subset of G. Oh wait. H is a subgroup. So we assume H is a subgroup if, okay, so only if. So we know that H is a subgroup. So we're trying to prove that H is not empty. Well, since H is a subset of G. How do I show that's non-empty? Well, it's a subset. How do I show it's non-empty? Okay, so okay, yes. No, that's not it. Yeah, the empty set is always a subset of anything, right? Empty set is a subset of anything. So oh wait, no, it's an if and only if. So we assume the first way that H is a subgroup. So first, since H is a subgroup, E is in H, thus H does not equal a null set. And let A and B be in H, since H is a subgroup. A star B is in H. A star, what is it? Since H is a subgroup, B inverse is in H, and A star B inverse is H inverse closure. Okay. So that's the proof one way, but now the other way, which I think is more interesting, we just sort of work backwards. So assume H is non-empty. And A star B inverse is in H. So what does that mean? Well, A star B inverse, what does that mean? I have to show that this means it's a subgroup. Well, first off, we've already shown it's non-empty. So, yay. Now we have to show that there are inverses for every element. So we need to want to show inverses and closure. So I mean, it basically shows that, but how do I logically prove that this means closure? Because these could come from G, right? These could come from G. So yeah, I'm just thinking I'll write a Laplace transform. Okay, so so it's not empty. We want to show inverses and closure. So in this case, we'd have to show that A and B are in H. So let's just say let A and B be in H. But A and B be in H. So since H is a subset, A inverse okay, hold up. Yeah, this is essentially closure. Oh. 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 Oh, okay, yeah, it is closure. Since where A, B in H. Since A and B are arbitrary, B inverse is in H for all B in H, and A star C is in H for all C. H. Thus, H is a subgroup. Okay. Yeah, we're almost done with this section. At around 9 hours, I'm gonna call it for this section. Maybe sooner. Maybe in 5 minutes. What do we got left? Okay, let's do this one. Okay. So assume G is group. Let G be a group and A be in G. Let C of A equal X in G such that A star X equals X star A. Prove that C of A is a subgroup of G. C of A is called the centralizer of A and G. Centralizer of A in G. That's cool to know. Wow, someone hasn't talked in 40 minutes. That's rough. Time really flies. Okay. So okay, so prove that it's a subgroup. So we need closure, non-empty, closed and inverses. So let's just show that it's not empty. Since G okay, I guess proof. Since E is in G, and A star E equals E star A, E is in C of A, so C of A is non-empty. Okay. Now you inverses or closure. So let A and B be in C of A. Okay. I think I'm getting my second wave of sort of energy. I think eating really helped. A and B be in C of A. So what will the last one be? Okay. Next one will be the last one. We can finish this easy. Okay, let A be and C. So A star X equals X star A. So now A star B, or no, let's do A star X star B equals X star A star B. So we have A star, because associativity, X star since associative, X star B equals X star A star B. So we switch these around. A star, since B is in C of A, we have B star X equals X star A star B. So A star B star X equals X star A star B. Thus closed. Okay, and now I have to prove inverses. on this little teensy line down here, if y'all can even see it. So I don't think that's too bad. A star oh yeah, left and right inverses. So that we have to prove the existence of such a number such that A star equals identity. Identity. Well, I think we can just do Laplace transform. No, we can't do that. Come on, I had it. Maybe I need more space. That's what I need. So we proved it was closed. I need more space, basically. So A star B star X equals B or X star B A star B, thus closed. Okay, so now gotta prove inverses. So we know E is in, but yeah, on B has to be in it. No, hold on. No, so let X be in G such that A star, oh wait, no, since A is in G, A inverse is in A has a unique left and right inverse. So A star A inverse equals E, but since A star A inverse equals A inverse star A equals E, A inverse is in C of A, and that proves it. It's a subgroup. Okay. Last question of subgroups. Then we move on to permutations. It's only 9. Like, I can easily get through that 3rd chapter. I mean, I have no clue how long it's gonna be. It's gonna be quite long. Alright. Okay, so we need to prove non-empty, closed, and inverses. So assume let G be a group and let Z, or not, just big Z of G equal set X in G such that A star X equals X star A for all A in G. Okay. Z is the center of G. Okay. Oh, what am I doing? Yeah. Okay, so prove that Z is a subgroup. Okay. Prove. Okay, so now we have to show non-empty. Well, since E is in G and A star E equals E star A, Z of G, E is in Z of G. That's part I. Or I guess I could save the line. E is in Z of G. Okay, next part I. We need closure. So let A, B be in Z of G. Okay, I'm gonna try to write small here, but we know A star X equals X star A. So A star X star B equals X star A star B. So A star X star B equals X star A star B. It's the exact same proof basically. So A star B star X equals X star A star B. So A star B star X equals X star A star B. And since A and B are so, and since G, or I guess, yeah, closed. Alright, now inverses. I think it's the same deal. Since, yeah, it's basically like the same proof. I'm not sure what's different. But yeah. Alright, we are moving on to groups and symmetry. Hello, theoretical nerd. Learn math and science, etc. I think I've heard of you. You're really smart. The theoretical nerd. I'm pretty sure you're like really smart, if I'm not wrong. So let's open. How do I go to your channel? I don't know how to go to your channel, but you know, alright, so we are just at about there. So right at around the oh yeah, your live source. You changed your name a little bit. Yeah, really smart. I am currently very tired. I might take a quick piano break. I don't know. But yeah, I'm gonna start learning about groups and symmetry. This section shouldn't be too long. I shall try to finish before 9:45, and then I will try to get as far as I can into the number theory section. We still have a long way to go, but number theory is where I'm going to end it for today. Tomorrow is just going to be group theory all day. Oh yeah, tomorrow is what we'll try to go from. Oh my goodness, not there. I mean, algebra is cool because you get to use a lot of fancy words that have you get to use fancy words. There we go. So yeah, tomorrow is basically just going to be all this. Generators, cosets, Lagrange, isomorphisms, Cayley, homomorphisms, groups, kernels, quotient groups, homomorphism theorem. Yeah. So I'm thinking I'm only going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections tomorrow. And that's if I don't, and on top of whatever I don't finish today of the number theory section, which shouldn't take too long because I already know a bit of number theory. I'm just a bit rusty on it. I'm not quick on my feet with number theory like most people are. Okay, I think it's time for a nice little piano break. I think it's I'm well due for a piano break. What do y'all think? Also, though, don't bite too many birds with one stone. Oh my goodness, my vocabulary is all mixed up. Don't bite off too much bread, more than you can chew. What? I don't know what I'm saying. Basically, don't do too much math, different maths. abstract algebra, I'd just say be very comfortable with linear algebra. That's basically it. You don't even need to have like advanced linear algebra. Oh, also proofs. Proofs, linear algebra, all you need. No calculus, no analysis, no anything. Just proofs and linear algebra. Yeah. So if you can do proofs, and if you know linear algebra, then you're set on abstract algebra. You don't even need to know. Yeah. Yeah. I mean that's why I'm doing it, because it's like other stuff like like topology. That's gonna require me to do some analysis. Like analysis isn't a hard prereq, but it really is basically, because you need to know like the motivation. It's the same deal for linear algebra, because technically you don't even need to know linear algebra for the stuff that's in abstract algebra. But it's basically like linear algebra is like applied abstract algebra. Same way like analysis is like applied topology. So that's why I really highly recommend. And you get to see some of those like abstract algebra concepts when you learn about vector spaces and stuff. So that's why I say, yeah, you could probably do algebra if you know proofs and linear algebra. That's all you need. Nothing too fancy. I mean, there is a lot of stuff. That's the thing, though, is that abstract algebra builds on itself. So when people say abstract algebra, it is such a broad field of math. Like, that's why I say undergrad %, because there's a lot more you can do with abstract algebra beyond undergraduate. Like, people research this stuff like for their entire lives, and it's crazy. So there's a lot to learn. I'm just doing the undergraduate curriculum. So yeah. Right now, if you just joined, I'm taking a piano break because I'm at the 9-hour mark and I am just dead inside. Maths genius or something, I guess. Haven't proven myself yet, so I gotta prove myself on the internet. Gotta come out of nowhere, be a mathematical prodigy, even though I was average at math like a few years ago. Math isn't my only thing. It's the one thing that I'm really ahead at. One thing I had resources to get ahead with. If I had resources for other stuff like business and philosophy, which is something I really interested in, I'd probably be ahead of those too. Alright, groups and symmetry. Let me start. Yes? Yeah, that starts it. Okay. 9 minutes! Yay! Alright. So, just as a number, groups can be used to measure symmetry. That's pretty cool. The application. This is introduced in chapter 14. The last chapter is the last chapter I do is all about symmetry, which is going to be cool. A group associated with an equation is associated with each equation, and this group characterizes a type of symmetry involving questions about the solvability of an equation will be studied in chapter 11, Galois theory. Alright. Now we look at how to associate each group with each figure in the plane. Let P denote the set of all points in a plane, and let M denote the set of all permutations of P. Preserve the distance between points. Thus P and Q are in P and Q, and mu is in M. And the distance mu of P and mu in P are equal to the distance P and Q. The permutations in M are called motions or isometries of the plane, basically moving things around in a plane. So if P is a fixed point in P, and then any rotation is a motion of the plane. Okay. The reflection of plane P through line L is a mapping that sends each point of P to the point Q, such that L is perpendicular to the bisector of segment PQ. I know y'all can't see all this. It's because it's all here. So this is a reflection. Should I use the 6th edition? If I were average, watch my How I Got Ahead at Math video. Basically just did 2 years of math per year until I got ahead. Basically. Because I was average, then I did 2 years of math per year. Basically. Because like, what was it? Like 8th grade I did Algebra 2 and Geometry. 9th grade I did, well I guess 9th grade I just did pre-calculus. I didn't do anything really extra. 10th grade I did calculus 1, 2, and 3, so multivariable calculus and differential equations. And now I'm in 11th grade. I'm doing linear algebra, and I did proofs, like how to prove stuff. Should you use the 6th edition? For, I don't know. It's up to you. You can ask other people. I mean, this book is nice. I'm only using it because I had it lying around. There are other books for abstract algebra that do like a more normal treatment that you would see. I mean, you'd still, this book does a pretty good treatment. I think if you went through this whole book like I am, you'll learn abstract algebra pretty good. Not like super deeply though. Like if you want a deep understanding of abstract algebra, I like how I said that, deep, then you're gonna want to pick up one of the more thicker textbooks, because this book is only this book, what I'm covering, is like not even 300 pages, and most abstract algebra textbooks, like I said, there's a lot to abstract algebra. They're pretty thick, like they can go up to the 500s. So if you want to use this book, it's nice. It's not, I mean, it's still thorough, but I guess it's because it covers like the bare basics. It doesn't go as deep. I guess that's like all I can really say. There are a lot of other books that go a lot deeper into abstract algebra. It's such a broad subject. It's so weird. Like it's weird how like deep abstract algebra goes, but it really is. It's like a crazy rabbit hole of awesomeness. So right now, I mean, if you want to use the 6th edition, it's up to you. You're not going to be missing out on much unless you like skip chapters. Then you would be missing out on a lot. Well, I say that because I'm skipping the last 2 chapters, which they're not useless. They're not abstract algebra. Okay, back to learning. Translations. A translation is something that moves P. Okay. Alright. Motion to the plane. Applied light. Okay. Alright, theorem. So, also, I would recommend you know how to read mathematics. Have I ever looked into knot theory? It's really topology related. So, I might take a look at it again once I know topology. Which has, I mean, technically knot theory, you don't need to know all sorts of prerequisites. But at the same time, it helps to know them. So, like, I guess. I have looked at category theory. That stuff's kind of interesting. I still don't know how on earth it's used in math. Because I looked at it from a programming perspective, kind of. I'm not really a theoretical computer science, though. Like, I appreciate it, but it's just not my thing. Theoretical computer science, not my thing. Alright, the set M of all motions, the set of all M of all isometries of a plane P forms a subgroup of a symmetric group on P. Proof. Let's see how it proves it. How long is this proof? Oh, it's pretty long. Okay, I'm gonna go ahead and write some of this down. Proof. Okay. For PQ in P, let D of PQ denote the distance. If is distance. Okay. If alpha is in the symmetric group on P, then A in M, and only if D of alpha of P, alpha of Q equals D of EQ. So first identity. Yeah. I is in M, just zero movement basically, keep it the same. Let alpha be in M. You have to go? Alright, see a live source. Alright. After this section, I'm not cutting off the I am cutting off the stream after this section, but I won't be done for the day. I think I'm gonna go ahead and do the other stuff. Alright. Alpha is in M, and beta is in M. If P and Q are in P, then I'm basically writing down this proof right now. If y'all are unaware of what I'm doing, I'm just taking notes. Then D of, let's see, alpha composed of B, P and alpha composed of B of Q equals D of alpha of beta of P. This is a nightmare to write down. Q, so many parentheses, equals D of beta of P and beta of Q equals D of P and Q. Oh, okay, since, and it's giving explanations. Since alpha is in M, beta of P is in P, and beta of Q is in P, since beta is in M, or is in M. Okay. Alright. Finally, let alpha be in M and PQ. Oh, okay, that's closed. Okay. PQ in P, then D of PQ equals D of I of P, I of Q equals D of alpha inverse of P of alpha inverse of Q. Okay, that makes sense. D of alpha inverse of P, alpha inverse of Q. Yeah. Okay. So now I use the image definition. So yeah, okay. So now definition. Okay, so now we have a definition. If T is a set of points in a plane, then MT the group of all motions leaving T invariant is called the group of symmetries. Or symmetry of T. Okay. Okay, so now let's get on to some problems for our last section of the stream. Don't worry, I will be doing a part 2 in about a little bit. Okay. I think I'm just gonna like take a shower or something just to rest. All right. Determine the group of symmetries of an equilateral triangle. Okay, so let's just look around and see what we get. So we have this reflection about the horizontal, or not horizontal, the vertical. Reflection about, what do I call this, a diagonal? And then reflection, what do I call it, reflection? Yeah. Through D2. Okay. Alright, so, and now we've got also our rotations, mu 0, mu 120, and mu 270. And I think that's it. Yeah. So that's our group right here. That's the group of symmetries for a triangle. Equilateral triangle, at least. Alright, now isosceles triangle. Always helps to draw a group. To draw a picture. So if we flip about this, it'll be the same, but we can't flip about that. It'll leave the base different. Okay, so we only have row V, and the rotations, or I guess mu 0. Mu 0. Yeah. I mean, it's still an isosceles triangle if you rotate it. That's the thing I'm confused about, if it's has to look exactly the same, because mathematically I'm guessing what I'm trying to look for is like determining things. I mean, I'll be better at this mathematically once I get to the last chapter, which is on symmetries. Let's see. What that is like. Sorry, I'm just looking ahead on the. Has to be exactly the same. Setup points needs to be same. The original. Okay. So, yeah, in this case, it is just rho v and mu 0. Okay. Group of symmetries of a regular pentagon. Okay. So, yeah, pentagon. Regular pentagon, so it's like this. Boom, boom, boom. Okay. So we can rotate it. What is it, like however many degrees this is? So it'll have like 5 like rotations you can put the mu 0, mu 360 over 5, which is a number. Uh, 360 over 5. I will figure that out real quick. That's 5 or hold on, that's 7 to 72. I totally knew that. Mu 72. Mu 144. Mu why am I using degrees? Just use radians. Yeah, this would be mu 2 pi over 5. Or I guess pi over 5. No, not pi over 5. 2 pi over 5. Mu 4 pi over 5. Mu 6 pi over 5. And mu 8 pi over 5. Okay. Those are our first rotations. Now let's see about diagonals. There's this one. There's this one. There's this one. There's that one. So there's 5 diagonals to rotate through. Or I guess a row, 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 D3, row, D4, row, D5. Okay. So, I mean, there's not many other questions about this. It's just a very basic thing on symmetries. So, like, I mean, yeah, it's pretty simple, really. Just trivial. Well, I will definitely get more into the symmetry stuff in the chapter 14, like the real depth of it. But for now, it's just sort of teasing you with the idea. With the letters, Oh, yeah, let me do the questions of the letters. I'll do that real quick and then I'll be done. Because everything else is just basically the same. So determine the of a square A, B, C, D corresponding to each motion in table 8.1. Table 8.1. Oh gosh. Okay. Determine the vertices. Okay, so I have to use this table where you have A, B, C, D, right? No. Oh god, this is confusing. Okay. Well, I think I can just sort of do this on my own. A, B, C, D. Permutation, right? You can rotate it, flip it. It's basically S4. No, it's not S4. What am I thinking? It's basically, oh, it's S2. S2. And because it's the same as okay, what am I thinking? What am I doing? I'm not doing anything. Oh, each letter in the alphabet. Okay, consider so A. Okay, so let's list out. This is pretty cool. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R. Yeah, I know, we're back in first grade, guys. Q, R, S, T, U, V, W, X, Y, and Z. Okay. So basically we have to find look, it's the alphabet. You can understand this, right? No, we have to find the each with the same group of symmetries. Determine the 5 sets of groups of symmetries. What? Okay, hold on. Into the motions. Okay. So we have motions, rotations. So mu 90, mu 180, mu 270, and mu 0. So which ones are in the same set? And the hint is that what is it? B, N, H, F are different sets. Basically, yeah, studying all of algebra. So I'm going to do what's called a pro gamer move and figure this out. And also, I'm ending this dream soon. So, okay, so I and H are the same. J, who would that be with? What is J the same as? K and Z are the same, or N and Z are the same. L and T are the same, or no, L and J are the same. L, J. So this, we're trying to split them up into 5 sets. So let's just list out what we have in different sets. So what are things that are the same as A? Let's see. K. X. Let's say X. Oh, list which symmetries they have. Oh, and then which ones? Okay. 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 So A, this is gonna take a while then, has, so I'll just list them right next to it. Mu 180, so we have mu 180, then mu 90, and then reflect about this diagonal, row D 1 and then row D2. Obviously it has mu 0 and mu, or I guess row H. This has row H, mu 0. This has row H, mu 0. Oh wait, no, it doesn't have row D1. What am I thinking? It has a row V. Alright. Yeah, I'll see you. I'll be here tomorrow. So E has row V, or no, row H. Okay, and then row unit 0. This one does not have row H. It just has mu 0. Mu 0. H has row V, mu 0, mu 180, row V. Then this one has mu 0, row H, mu 180. This one just simply has mu 0. This one has mu 0 and row H. This one has just mu 0. M has mu 0, mu 180, and row V. n has row mu 0, not row v, oh yeah, mu 0 and you flip along its diagonal. I think it's, yeah, row d, or no, row 1. If you flip along this diagonal, it's one of the diagonals, row 1. If you flip along the diagonals, row 1 or row 2, one of the diagonals, I forget. O, this one has mu 0, and I guess it has all the other symmetries, all of them basically. Mu 180. Has all of them. This one has mu 0 and just nothing else. This one, same deal, nothing else. R, it's just mu 0. S, just mu 0 and row H. T is just mu 0 and row H and row V and no, it's not row H, it's row V and mu 180. Yeah, this one has mu 180, mu 0, row V, same thing, it's just a double V, same thing, has everything basically, everything is O, so just N, Y is just mu 0, O, row, V, and wait, 180. And Z is the same as N. So the sets are A, H, I, M, U, V, W, and then we have, oh boy, I gotta end the stream soon. Then we have B, C, D, K, S, wait, did I include E? Oh wait, no, horizontal, yeah, E should be in here, D, E, S, and that's basically it. Oh, Y. Okay, the second set, we have N, O, X, Z, then we have F, H, Uh-oh. It just got quite a few. Well, we have F, L, J, T, R, Q, P. Okay, yeah, that's basically it. Alright, bye. What hour am I doing this? All day. All day. Okay. Alright. I'm done with chapter 2. Celebrate. Alright, so I'm gonna go ahead and split here and pause. So that's it for the stream. I might get back on later, or I could just like time my turn the time on. No. If I ever want to submit this to speedrun.com, I'm gonna want to but I probably, this is nowhere near good enough to send to speedrun.com, so I might just time it without turning on the stream, and then tomorrow I'll turn on the stream again, or I might just turn on the stream just for a little bit tonight, because I do want to go to bed soon. Actually, I might just call it for today. It's already 10 o'clock. If I want to get up early tomorrow, I'm gonna have to go to bed soon. So yeah, so tomorrow we're gonna try to go through number theory and group theory both in one day. Yeah, hopefully we won't have too many problems. So yeah, that's basically it. See ya. Yep. Thanks to y'all for watching.